Hello there, and welcome to Sleepy Science Vault. There was a time, not so long ago in the grandest sense, when the universe had no darkness at all. Not because it was filled with stars, or galaxies, or the soft warm glow of distant suns, but because space itself had not yet learned the difference between light and shadow. In those first extraordinary moments after the Big Bang, everything was energy. Pure, blazing, incomprehensible energy, compressed into a space smaller than anything you can hold in your mind. 1 second after the universe was born, the temperature was around 10 billion degrees. The entire cosmos was a seething, radiant fog. Not empty space with things floating in it, but space that was itself on fire. Protons and neutrons were only just beginning to form. Electrons were still too energetic to settle anywhere. Light existed, but it couldn't travel. It was trapped, bouncing endlessly through a plasma so dense that even a photon couldn't move more than a short distance before being absorbed and re-emitted. The universe, in those first moments, was blinding and yet completely dark to any observer. Because there was no distance. There was no view. There was only heat and pressure, and an almost incomprehensible unfolding. Then something remarkable happened. For roughly the first 380,000 years, the universe expanded. It stretched, slowly, steadily, and as it stretched, it cooled. And one day, after nearly 400 millennia of that dense, radiant fog, the temperature finally dropped to around 3,000 degrees. Electrons, at last, could slow down enough to be captured by atomic nuclei. Atoms formed for the first time. And in an event astronomers call recombination, the fog cleared. Light was freed. For the first time in the history of everything, a photon could travel in a straight line without being immediately swallowed. The universe became transparent. And that very first light, released in that single moment of clearing, is still traveling today. We call it the cosmic microwave background. It surrounds us even now, a faint whisper of radiation arriving from every direction at once. The oldest light we will ever detect. But that was the beginning. This story is about the end. Because the universe that opened with such brilliance will not stay bright forever. When scientists and philosophers speak of the last light, they are speaking of something very specific and very final. Darkness, it turns out, is not simply the absence of a lamp, or the setting of the sun, or the turning off of a light in a room at night. At the deepest level, darkness is the void left behind when photons depart, when light is no longer being created, when the last sources of energy have spent themselves completely, and what remains is a silence so total that not even a single particle carries enough energy to illuminate anything at all. We are not there yet. We are still in a universe burning with possibility, surrounded by hundreds of billions of galaxies, each containing hundreds of billions of stars. But the universe has a structure to its life. A shape to its story. Cosmologists have described the full lifespan of the universe as 5 distinct eras, 5 ages, each one almost incomprehensibly longer than the last. The first is the primordial era, the fiery birth we've just described. The second is the stelliferous era, the age of stars. This is the era we live in now, a period so rich with light and warmth and nuclear fire that it can be easy to assume this is simply what the universe is. But the stelliferous era will end. Stars will exhaust their fuel. No new ones will form. And then comes the degenerate era, a long dimming age of cooling white dwarfs and fading stellar remnants. After that, the black hole era, where even those cold embers are gone, and only black holes remain, slowly radiating away in a process so gradual it makes geological time feel like a heartbeat. And finally, the dark era. An epoch with no stars. No planets. No meaningful energy exchange of any kind. Just an expanding, cooling, emptying cosmos, drifting further and further apart, with nothing left to say. This long arc, from blazing birth to infinite quiet, has three possible endings, according to our best understanding of physics. In the first, the universe expands forever. Space continues to stretch outward, matter thins to near nothingness, and what remains is a cold and featureless darkness without horizon or edge. In the second possibility, a mysterious force, what some physicists call the Big Rip, accelerates that expansion so violently that even atoms are eventually torn apart, the very fabric of matter unraveling before it can simply fade. And in the third, the expansion reverses. Gravity reasserts itself over cosmic scales. The universe, in a mirror of its beginning, collapses back inward into what some call the Big Crunch, not an end in darkness, but an end in unimaginable fire, the cosmos folding back into the point from which it came. All three of these endings share one thing. At some point, the lights go out. What we are really talking about, when we speak of the last light, is a question that reaches far beyond astronomy or physics. It is a question about meaning, about time, about what it means for something to exist at all in a universe that began in a blinding flash, lived for trillions upon trillions of years in radiant warmth, and will one day know a silence so absolute that even the memory of light will have no one left to remember it. The universe is approximately 13.8 billion years old. And it is still, by its own vast standards, quite young. We are here, in these early hours, looking up. The light that was freed at recombination did not simply vanish into a waiting universe. It traveled. And it is still traveling now, arriving at our instruments from every direction at once, carrying with it the imprint of everything that the universe looked like in that earliest moment of clarity. We call it the cosmic microwave background. And it is, in a very real sense, a photograph, the oldest photograph that exists or ever could exist. Not a picture of stars, or galaxies, or anything we would recognize as a landscape. It is a picture of the infant universe itself, taken in the moment the fog cleared, stretched and cooled by billions of years of cosmic expansion until those first warm photons have become cold microwave radiation, arriving today at just under 3 degrees above absolute zero. Satellites have mapped it in extraordinary detail. And what they found are tiny fluctuations, small variations in temperature, 1 part in 100,000, that represent the seeds of everything that would come later. Every galaxy, every cluster, every filament of structure in the observable universe grew from those faint ripples in the ancient light. It is humbling to think that the texture of the night sky, the particular arrangement of everything we have ever seen or ever could see, was written into the universe in its very first moments, encoded in the light that was released when the cosmos finally learned to be transparent. But after that light was freed, something unexpected followed. Silence. Not metaphorical silence, literal cosmic darkness. The universe, having produced its first great release of light at recombination, then entered a period that astronomers call the cosmic dark ages. The fog had cleared, yes. Photons could travel freely. But there was nothing to see. The gas that filled the universe, mostly hydrogen, had cooled and spread too thin to glow. No stars had formed yet. No galaxies existed. There were no sources of new light anywhere in the observable cosmos. For perhaps 200 million years, the universe was dark. That number is worth sitting with. 200 million years of darkness, interrupted by nothing. The universe existed, matter was there, gravity was working, gas was slowly gathering, but if you had been present somehow, floating in that expanding void, you would have seen nothing at all. Not a single star, not a distant flicker, not even the faintest red glow on any horizon. Just the cooling remnant radiation of the Big Bang, growing dimmer and dimmer as space expanded around it, and the slow, patient work of gravity pulling invisible matter toward invisible matter in the dark. This period is one of the least understood in all of cosmology, precisely because there was no light to carry information to us. We cannot directly observe what happened in those 200 million years. We can only model it, and infer it, and wonder at it. And then, slowly, a change began. The densest regions of gas, the places where matter had gathered most tightly under the pull of gravity, began to collapse inward. As the gas compressed, it heated. And at the centers of these collapsing clouds, where the pressure and temperature finally crossed a threshold that the universe had been working toward since the beginning, nuclear fusion ignited for the first time. The first stars were born. Astronomers call this moment the cosmic dawn. And it was, in a very real sense, the second great illumination of the universe, the first being the release of the cosmic microwave background, and this being the moment when new, self-sustaining sources of light came into existence for the first time. Those first stars were nothing like the sun. They were enormous, hundreds of times more massive than anything that forms today, burning so hot and so bright that they poured out intense ultraviolet radiation in quantities that the universe had never seen. And that radiation began to do something critical. It started to ionize the hydrogen gas around each new star, stripping electrons from atoms and slowly making the surrounding gas transparent to the new light streaming outward. This process, the reionization of the universe, unfolded over hundreds of millions of years. Bubble by bubble, region by region, the ultraviolet light from the first stars carved out expanding spheres of transparency in the surrounding neutral gas. These bubbles grew, and merged, and overlapped, until eventually the vast majority of the intergalactic medium had been reionized. The universe became, for the second time, transparent, but now in a fundamentally different way. Now it was transparent because stars were actively illuminating and ionizing it, rather than simply because the fog of the early universe had thinned. We live in that transparent universe today. the light from distant galaxies reaches our telescopes across billions of light-years of largely clear intergalactic space because the cosmic dawn finished its work and left behind a cosmos capable of being seen. What made all of this possible, though, what allowed the first stars to form at all, and what shaped the large-scale structure of the universe into the intricate web of galaxies and filaments we observe today, was something we cannot see. Dark matter. The name itself is more poetic than technical. It is not dark in the way that a shadow is dark, or the way that a night sky between the stars is dark. It is dark because it does not interact with light at all. It does not emit photons. It does not absorb them. It does not reflect them. Every instrument we have ever built to detect light, in any wavelength, is completely blind to it. And yet it is everywhere. Roughly 85% of all the matter in the universe is dark matter. The ordinary matter that makes up stars, planets, gas clouds, and every atom in your body accounts for only about 15% of the total. The universe is, by mass, predominantly made of something we cannot see, cannot touch, and do not yet fully understand. What we do understand is what it does. Dark matter responds to gravity, it has mass, and it pulls on other matter, and it is pulled in return. Long before ordinary matter had cooled and condensed enough to form the first stars, dark matter was already gathering into vast structures. Cosmologists sometimes call these structures the cosmic scaffolding, an invisible skeleton of gravitational potential that organized the universe on its largest scales, drawing ordinary matter toward it and shaping it into the patterns we observe. Without dark matter, there may have been no galaxies. The ordinary matter alone may not have been dense enough, or clustered enough, to collapse into stars at all on the timescales we observe. Dark matter concentrated first, and then gas fell into the gravitational wells it created, and stars formed within those wells, and galaxies took shape around them. The brilliant cosmic web of light that fills our night sky was, in a very deep sense, first sketched out in the invisible. It is a remarkable thing to consider. The architecture of everything we can see, every galaxy cluster, every galactic filament, every bright thread of stars stretching across hundreds of millions of light years, was drawn in matter that produces no light of its own. The universe built its visible structure on an invisible foundation. But here is where the story becomes stranger, and stranger still. Some physicists have proposed that alongside ordinary light, the photons we detect, the electromagnetic radiation that carries all the information we have ever gathered about the cosmos, there may exist another kind of light entirely. Something called dark photons. Dark photons are theoretical particles, proposed as force-carrying partners within the dark sector of the universe, the hidden world of dark matter and whatever forces govern it. In the same way that ordinary photons are the carriers of the electromagnetic force between ordinary charged particles, dark photons may carry a corresponding force between dark matter particles. They would be, in a sense, the light of the invisible world. What makes this idea so extraordinary is not just the concept itself, but what dark photons are thought to be like. They would be extraordinarily light, carrying almost no mass at all, if any. And crucially, they would not be entirely isolated from the world we can observe. physicists believe that dark photons may oscillate, that they may flicker, at a quantum level, back and forth between being dark photons and being ordinary photons. This process, called kinetic mixing, would represent a faint, probabilistic bridge between the dark sector and our own. A dark photon traveling through space might, at any moment, spontaneously convert into an ordinary photon, an observable particle of light, emerging from a source of darkness. The probability of any individual conversion is vanishingly small. But the universe is vast, and the dark sector, if it exists as theorized, contains an enormous amount of energy distributed across all of cosmic space. Some researchers have suggested that these conversions might contribute to the diffuse background radiation we observe, adding faint, difficult-to-detect signals to the cosmic web of light. Others have proposed that dark photons might interact with the hot, ionized plasma of the cosmic web, the vast filaments of gas that connect galaxy clusters across hundreds of millions of light years, in ways that leave subtle, measurable imprints. That web of gas, the cosmic web, is itself a spectacle worth pausing on. It is one of the largest structures in the observable universe, a network of filaments, sheets, and nodes, where galaxy clusters sit at the intersections like bright cities connected by dim roads. The gas that fills those filaments is hot, in some places reaching tens of millions of degrees, glowing faintly in X-ray wavelengths that only our most sensitive space telescopes can detect. And it is in this hot, luminous environment that dark photons, if they exist, would be most likely to interact with the ordinary world, potentially heating the gas, or adding a subtle glow to the filaments, or leaving signals that future experiments might finally be sensitive enough to detect. We have not confirmed the existence of dark photons. They remain a theoretical prediction, an elegant proposal that attempts to give structure and logic to the dark sector, and to answer the question of what force governs the behavior of dark matter the way electromagnetism governs ours. But the search is active and ongoing. There is something deeply poetic in the idea that the invisible architecture of the universe, the scaffolding that made all visible light possible, might itself be shot through with its own kind of light. A parallel luminosity, forever hidden from ordinary eyes, traveling through the dark sector the way our photons travel through the bright one. Two universes of light, occupying the same space, nearly unable to see each other. We built our entire understanding of the cosmos from the photons that reached our eyes, and then our instruments. But if dark photons exist, if there truly is a mirror kind of light moving through the hidden structure of reality, then everything we have ever called the observable universe is only half the picture. Perhaps less. The universe that began in fire, and passed through 200 million years of darkness, and then ignited into the cosmic dawn, that universe is richer and stranger and more layered than any single wavelength of light can show us. And the story of its last light is not simply about when our stars burn out. It is also a question of whether there is another light, in another sector, that we have not yet learned to read. There is a moment in the life of any fire when it burns at its brightest. Not the moment it is lit. That first ignition is chaotic, unsteady, still finding its shape. And not the long slow dimming that follows, when the fuel is nearly spent and the light has softened to something quieter. There is a middle moment, a peak, When everything the fire has to offer is present all at once, when the heat is greatest, the light most generous, and the air around it seems to hum with warmth. The universe had that moment. It was not recent. By human standards, by any standard that feels intuitive or manageable, it was almost incomprehensibly long ago. Roughly 10 billion years in the past, when the cosmos was only about 3 to 4 billion years old, the universe reached what cosmologists call the peak of star formation. Galaxies across the observable cosmos were producing new stars at a rate that dwarfs anything happening today. The raw materials were abundant, vast clouds of cold hydrogen gas, gathered into galaxies that were still young enough to have enormous reserves of fuel. Gravity was working efficiently. Collisions between galaxies were more frequent, compressing gas and triggering bursts of stellar birth that could produce thousands of new stars in a single galaxy in a single year. This period is sometimes called cosmic noon. And it is, in the most literal sense, when the universe was at its most luminous. Think about what that means in full. Every star that forms is a new source of light, a new nuclear furnace, converting hydrogen into helium and releasing energy as photons that travel outward in all directions. At cosmic noon, those furnaces were being built faster than at any other point in the history of the universe. New stars were being added to galaxies in staggering numbers. The total amount of light being produced across all of observable space was at its absolute maximum. If you could have been there, floating somewhere in the intergalactic medium 10 billion years ago, in a universe roughly a third of its current age, the night sky would have looked nothing like ours. Galaxies were more numerous in every direction, closer together on average, brighter, bluer, more actively forming stars. The universe would have felt, by any measure, more alive. That peak has passed. We now live more than 10 billion years past cosmic noon, in a universe that has been declining in its star-forming activity ever since. The rate at which new stars are born across the cosmos has been falling for billions of years, and it continues to fall. The great reserves of cold gas that fueled the early universe have been used up, dispersed, or locked away inside stars and stellar remnants. The conditions that made cosmic noon possible, abundant fuel, frequent galaxy mergers, dense star-forming clouds, are simply less common now. This is not a sudden change. It is a slow, long, structural decline, the kind that unfolds across billions of years and is invisible on any human timescale. But it is real, and it is measurable, and it tells us something important about where the universe is in its own story. There are 3 clear indicators that the era of great stellar activity is behind us. The first is the direct measurement of star formation rates across cosmic time. By observing galaxies at different distances, and therefore different points in the past, since the light from distant galaxies takes billions of years to reach us, astronomers can piece together a history of how quickly stars were forming at any given epoch. That history shows a clear rise to a peak around 10 billion years ago, and then a long, sustained decline that brings us to the present. Today's star formation rate, averaged across the observable universe, is roughly 10 times lower than it was at cosmic noon. The second indicator is the color of galaxies. Young, actively star-forming galaxies tend to be blue. This is because the most massive young stars burn extremely hot and emit most of their light in the blue and ultraviolet range. When a galaxy is forming lots of new stars, those hot blue stars dominate its light. But massive stars burn out quickly, in millions of years rather than billions. As a galaxy's star formation slows, those brilliant blue stars disappear, and what remains are the longer-lived, cooler, redder stars. Over time, a galaxy transitions from blue to red. And across the observable universe, we see exactly this trend. The galaxy population as a whole is becoming redder as star formation fades. The third indicator is the cold gas content of galaxies. Stars form from cold molecular hydrogen gas. As galaxies use up their gas reserves to make stars, and as that gas is expelled by supernova explosions and the radiation pressure of massive stars, the available fuel for future star formation decreases. Surveys of the molecular gas content of galaxies across cosmic time confirm what the star formation rates suggest. The universe's fuel supply is being spent, and the rate of replenishment is not keeping pace. Taken together, these three lines of evidence paint a consistent picture. The universe, in a cosmological sense, has passed through its most productive period. The lights are not going out yet, not by any means. There are still hundreds of billions of galaxies, each containing billions of stars, and star formation continues throughout the cosmos even today. But the trajectory is clear, and it has been clear for a long time. Some cosmologists have described this phase of the universe's life with a quietly evocative phrase. They call it the nodding off phase. It is not sleep, and it is not death. It is that long, gradual transition between full wakefulness and rest, when the energy is still there, when the world around you is still present, but when the intensity has softened, and the pace has slowed, and everything is trending, gently and inevitably, toward quiet. The universe is not dramatically dying. It is winding down. Slowly, over timescales so vast that no civilization could ever witness the full arc, the cosmic fire is burning lower. And it has already been doing so for a very long time. Here is a figure that, once you hear it, has a way of staying with you. The universe today is already roughly half as bright as it was at its peak. Not in terms of the light we can see from Earth on any given night, that depends on many local factors. But in terms of the total energy output of the observable universe, the integrated light of all its stars and galaxies measured across all wavelengths, the cosmos is producing approximately half the light it produced at cosmic noon. Half the light. In a universe that still contains hundreds of billions of galaxies. That figure speaks to how extraordinary the peak truly was, and to how far the long decline has already progressed. We did not arrive at this moment at the beginning of the dimming. The dimming has been underway for billions of years. We are living in a universe that has already crossed the halfway point of its luminous life, and is continuing, steadily, to grow quieter. This is not cause for distress. The stars that remain will burn for billions of years more. The Sun has approximately 5 billion years of hydrogen fuel remaining. Life, and light, and warmth are not going anywhere on any timescale that has meaning for us, or for any civilization we might imagine. But understanding the arc of cosmic history, where the universe has been, and where it is going, changes something in the way this moment feels. We are here, in the long afternoon. Not the blazing noon, and not the dark of night. The afternoon, still bright, still warm, still full of everything that makes a universe worth inhabiting, but already past the peak. Already in the gentle, golden, elongated hours of a day that will eventually end. And yet, even in this dimming universe, the amount of light that still surrounds us is staggering. When astronomers look out at the night sky and attempt to count and measure every source of light they can detect, every galaxy, every star, every luminous object within the reach of our best telescopes, they face a surprising problem. The light they can account for does not add up. Roughly 80% of the light that should be filling the universe cannot be explained by the sources we can see. This discrepancy is not a minor rounding error. It is not a gap that a slightly better telescope would close. It is a fundamental puzzle in observational cosmology, and it goes by the name of the missing photons problem, or sometimes the ultraviolet photon budget problem. The basic question is this: when you count up all the ionizing radiation that known sources, galaxies, quasars, active galactic nuclei, should be producing, and then compare that to the amount of ionization we actually observe in the intergalactic medium, there is a significant shortfall. The universe appears to be more ionized than it should be, given the sources we have identified. Something is producing more photons than we can account for. Where is the missing light coming from? The answer, as of our best current understanding, is almost certainly galaxies, but not the bright, easily detected ones. The missing photons likely originate from the enormous population of small, faint, low-luminosity galaxies that are difficult to detect individually but may be present in vast numbers throughout the universe. These galaxies are too dim to appear in most surveys as distinct objects, but if enough of them exist, their collective light could fill the photon budget and resolve the discrepancy. This is closely related to a broader measurement that astronomers call the cosmic optical background, the total integrated brightness of the sky in visible light wavelengths, coming from all sources at all distances across the entire observable universe. Measuring the cosmic optical background is an extraordinarily difficult task, because you must first subtract all local sources of contamination: the light of the sun, the glow of the Milky Way, the scattered light of interplanetary dust, and what remains is incredibly faint. The actual brightness of the extragalactic optical background is measured in units called nanowatts per square meter per steradian, and the values involved are almost poetically small. 11 nanowatts per square meter per steradian. To put that in some perspective, a single LED nightlight produces millions of times more light per unit area than the entire integrated brightness of the extragalactic universe as seen from our location. The combined glow of hundreds of billions of galaxies, stretched across 13 billion light-years in every direction, amounts to something your eye could not detect against a dark wall. And yet that measurement, that faint and almost ghostly signal, contains within it the light of everything, every star that has ever burned in the observable cosmos, every photon that has traveled billions of light-years to contribute its infinitesimal fraction to the total. There is something in that number that feels like it should be larger, and something that feels exactly right. The universe is vast beyond easy comprehension, but it is also mostly empty, and mostly old, and the light from distant sources is dimmed by the expansion of space itself. The 11 nanowatts is not a disappointment. It is an honest accounting. And here is what makes it even more interesting. When scientists have carefully measured the cosmic optical background and compared it to the expected contribution from all the galaxies we can catalog and count, the numbers, while close, have shown some tension. For a time, there appeared to be a slight excess of light beyond what known galaxies could account for. This raised the possibility, considered seriously for a period, that there might be some unknown source of light in the universe, some diffuse, unidentified emission filling intergalactic space from an origin we had not yet discovered. The candidates proposed were varied and imaginative. Decaying dark matter, perhaps, dark matter particles with a finite lifetime that release photons as they decay, producing a faint, uniform glow distributed throughout the cosmos wherever dark matter resides. Or axion-like particles, theoretical cousins of dark photons, converting slowly into light as they travel through intergalactic magnetic fields. Or perhaps truly ancient stars formed before the first galaxies, scattered through the universe before structure fully assembled, contributing a diffuse stellar background that no telescope has yet resolved into individual sources. The mystery captured genuine scientific attention, because the implications of an unknown light source would have been extraordinary. A diffuse cosmological glow without a known origin would have pointed toward new physics, new particles, new processes operating quietly throughout the universe that our current models had entirely missed. But as measurements improved, as better instruments and more careful analysis refined the accounting, the excess has largely dissolved. The current best evidence suggests that the cosmic optical background can be explained by known sources, primarily galaxies, including the faint and numerous low-luminosity galaxies that earlier surveys had undercounted. There does not appear to be a mysterious unknown light source filling the universe with extra photons. The universe, it seems, is exactly as bright as its known contents should make it. And that brightness, already half of what it once was, continues its long and patient decline. There is a quietness to all of this that becomes, with time, almost meditative. The universe had its blazing noon. It filled the cosmos with light, built galaxies and stars and the intricate large-scale architecture that makes it what it is. And now it rests in a long, slow, golden afternoon that will eventually shade into evening, not for billions of years, but eventually. The trajectory is set. We are fortunate, in a way that is difficult to fully articulate, to be here in this particular era. Late enough to inherit a universe of breathtaking complexity and structure. Early enough to still be surrounded by stars, billions upon billions of them, burning in every direction, filling our sky and our instruments with light that took millions or billions of years to reach us. The universe is still speaking, still radiating, still burning. Just not quite as loudly as it once did. Across the entire history of the observable universe, from the first moment light was freed at recombination to this very second, an almost inconceivable number of photons have been produced. The best estimates place the total number of photons ever generated by stars alone, not counting the cosmic microwave background, not counting other sources, just starlight, at somewhere around 10 to the power of 84. That is a 1 followed by 84 zeros. A number so large it has no meaningful analogy in everyday experience. The total number of atoms in the observable universe is estimated at around 10 to the power of 80. The number of photons ever produced by stars is larger than the number of atoms in the entire observable universe by a factor of 10,000. Every star that has ever burned, every nuclear reaction at every stellar core across every galaxy across all of cosmic time, has contributed to that count. Each photon was a small packet of energy, launched outward at the speed of light, carrying warmth and information in every direction. And yet, for all that staggering abundance, the light we can actually observe today represents only a fraction of what was ever made. Not because photons decay or disappear in the way that matter can, but because the universe is very old, and very large, and the physics of space itself works quietly against the survival of light in any useful form. Understanding why light slowly disappears is one of the more subtle and beautiful ideas in all of cosmology. It does not happen suddenly. It does not require anything dramatic. It is simply the natural consequence of the universe being what it is. The first thing to understand is that photons lose energy as the universe expands. This is not a collision, not an absorption, not any kind of interaction with matter. It is a consequence of the fact that light is a wave, and the wavelength of that wave is stretched by the expansion of space itself. As the universe grows, the distance between the crests of a light wave grows with it. A longer wavelength means lower frequency, and lower frequency means less energy. This is what we call cosmological redshift, the gradual draining of energy from photons simply by virtue of their traveling through an expanding cosmos. The cosmic microwave background is the most striking example of this process. Those photons were originally released at a temperature of around 3,000 degrees. They were infrared invisible light photons, warm and energetic. But in the 13.8 billion years since recombination, the universe has expanded by a factor of roughly 1,000. And those photons have been stretched accordingly. They now arrive as microwaves, carrying only a tiny fraction of their original energy. They have not disappeared. They are still here. But they are cold and quiet and carry almost nothing of what they once were. Every photon traveling through the universe is undergoing this process continuously. Starlight that left a distant galaxy a billion years ago arrives at our instruments slightly redder, slightly less energetic than when it was emitted. Light that left 10 billion years ago is redder still. The expansion of space is a slow and patient thief, draining energy from every photon on every journey. But here is something important, and perhaps surprising. Photons themselves do not decay. Unlike many particles in physics, photons have no intrinsic lifetime. An isolated photon in empty space will not spontaneously cease to exist. It will not break down into other particles, or fade in the way that a radioactive atom fades. As far as our best physics tells us, a photon left entirely to itself, traveling through a perfectly empty universe with no expansion, would continue traveling forever without any change at all. What happens to light is not decay. It is something more subtle, a combination of energy loss through expansion, absorption by matter, and most critically, an increasingly fundamental barrier that the universe is constructing around every observer. That barrier has to do with where light can and cannot reach. Even though photons travel at the speed of light, the fastest anything in the universe can move, they cannot necessarily reach every destination in an expanding universe. The key is that space itself is expanding, and in regions far enough away, it is expanding faster than light can cross it. This is not a violation of relativity. The speed of light is a local limit. Nothing passing through space faster than light remains intact. But space itself can stretch at any rate, and in our universe, driven by dark energy, the expansion is accelerating. This means there is a distance beyond which light emitted today will never reach us. Not because it will run out of energy on the way, not because anything will stop it, but simply because the space between us and that source will expand faster than the photon can cross it. The photon will travel toward us forever and never arrive. That boundary is called the cosmological event horizon. And because the expansion of the universe is accelerating, that horizon is not moving outward to include more of the universe over time. In a universe with accelerating expansion, the event horizon actually represents a shrinking sphere of causal contact. Future observers will be able to see less of the universe than we can today, not because their telescopes are worse, but because more of the universe will have receded beyond the reach of light. This brings us to the Hubble parameter, the value that describes the rate at which the universe is expanding. It is often written as a speed per unit distance, currently around 70 kilometers per second per megaparsec. What that means in practice is that for every megaparsec of distance, roughly 3.25 million light-years, the universe is expanding at an additional 70 kilometers per second. Double the distance, double the recession speed. At a certain distance, recession speeds reach the speed of light, and beyond that, no signal can ever reach us. The Hubble parameter itself changes over time. In the early universe, it was much higher. The expansion was fast, driven by the enormous energy density of the hot early cosmos. As the universe aged, the Hubble parameter fell as matter and radiation diluted. But dark energy, which behaves differently from matter and radiation, does not dilute as space expands. It appears to be a constant property of space itself, or something very close to it. And as matter becomes more and more dilute while dark energy remains roughly constant, dark energy's influence grows, and the expansion accelerates. If dark energy remains constant into the far future, and current evidence suggests it will, then the universe will continue accelerating indefinitely. And the consequences for the visibility of the cosmos are profound. In the very far future, galaxies that are currently visible to us will drift beyond our cosmological horizon. Not abruptly, not in a single dramatic event, but gradually, as their recession speeds creep up toward and past the speed of light. Their light will become increasingly redshifted, increasingly dim, and eventually frozen, arriving at an infinitely slow trickle, each successive photon taking longer and longer to cross the widening gulf. From the perspective of an observer here on Earth, or wherever observers might exist in the future, those distant galaxies will appear to freeze in time. Not disappear instantly, but slow, redden, and asymptotically approach a final image that never quite reaches them. A galaxy caught on the edge of the horizon would appear to halt, suspended in its last visible moment, growing dimmer and redder over eons until it fades below any detectable threshold. The Milky Way's nearest major neighbor, the Andromeda Galaxy, is gravitationally bound to us. It will eventually merge with our own galaxy, and that merger is not threatened by cosmic expansion. Gravity holds them together against the general flow of space. The same is true for the local group of galaxies, the small cluster of a few dozen galaxies of which the Milky Way and Andromeda are the largest members. Gravity wins locally. But beyond the local group, beyond the gravitational reach of our immediate cosmic neighborhood, every galaxy is moving away from us, and accelerating. In perhaps 100 billion years, a future astronomer looking out from whatever remains of our galaxy would see no other galaxies at all. Not because they have been destroyed, but because they have all crossed beyond the horizon, their light unable to make the crossing against the relentless expansion of space. That future astronomer would live in a universe that appeared, to all observational evidence, to contain exactly one galaxy. They would have no way of knowing that the universe had once been full of hundreds of billions of them. The evidence would be gone, carried beyond the horizon, unreachable and undetectable. We are fortunate to live in an era when the universe is still legible. And then there are the stars themselves, the individual points of light that have filled every human sky since the first eyes looked upward. They, too, are changing. Slowly, on timescales that dwarf the entirety of recorded history, but changing nonetheless. Our own sun is a useful place to begin. It is a middle-aged star, approximately 4.5 billion years old, with roughly 5 billion years of hydrogen-burning life remaining. During that time, it will not stay constant. Stars like the Sun are not static furnaces. They gradually brighten over their lifetimes as helium builds up in their cores, raising the core temperature and increasing the rate of fusion. The Sun today is about 30% brighter than it was when Earth first formed. And it will continue to brighten. Over the next billion years or so, the Sun's increasing luminosity will have significant consequences for Earth. The added heat will eventually push Earth's surface temperature beyond the range where liquid water can persist. The oceans will begin to evaporate. The water vapor, a potent greenhouse gas, will accelerate the warming, potentially triggering a runaway greenhouse effect that transforms Earth into something resembling Venus. This is not a sudden catastrophe. It is a slow transition, unfolding over hundreds of millions of years. But it is coming, written into the physics of how stars age. Beyond that, in approximately 5 billion years, the Sun will exhaust the hydrogen in its core. The core will contract in heat, while the outer layers expand enormously, and the Sun will become a red giant, swelling outward to perhaps 100 times its current size, engulfing Mercury, possibly Venus, and coming very close to, or even reaching, the current orbit of Earth. Whatever remains of our world by then will be scorched beyond recognition. But even in this expansion there is light. An enormous, glowing red giant, shining hundreds of times more brightly than the Sun does today, filling the inner solar system with a ruddy luminosity unlike anything that currently exists here. In its final stages, the Sun will shed its outer layers in a beautiful expanding shell of glowing gas, a planetary nebula, while the core that remains will be a white dwarf, a dense, Earth-sized remnant of stellar ash, no longer fusing hydrogen or anything else, simply radiating the heat it accumulated over its long lifetime. That white dwarf will glow for billions of years. Not from nuclear reactions, but from pure thermal emission, the slow release of stored heat into the surrounding darkness. It will cool over time, shifting from white to yellow to orange to red, and eventually, over timescales so vast that the current age of the universe is only a fraction of the journey, it will cool to the point where it no longer emits visible light at all. A black dwarf. A cold, dark, dense remnant of what was once a star. And yet, the universe is not yet old enough for any black dwarf to exist. The cooling time required to bring a white dwarf to that final dark state is estimated at longer than the current age of the universe, perhaps by a significant margin. Every white dwarf that has ever formed is still glowing. Every stellar remnant of this kind is still warm. The universe is, even now, too young for its own embers to have fully cooled. The stars that are still alive today span an enormous range of lifetimes. The most massive stars burn hot and fast, exhausting their fuel in just millions of years. They are brilliant and profligate, spending their energy quickly and leaving behind neutron stars or black holes. The sun-like stars burn for billions of years. And the smallest stars, the red dwarfs, burn so slowly, so efficiently, at such low temperatures, that their lifetimes stretch to trillions of years. Red dwarfs are the most numerous type of star in the universe. They make up perhaps 70 to 80% of all stars. And they will be the last stars burning in the stelliferous era, long after every sun-like star has expanded, shed its layers, and collapsed into a white dwarf. Long after every massive star has detonated in a supernova. Long after the Milky Way has settled into whatever form it takes after its merger with Andromeda. The red dwarfs will still be burning, quietly, in the long dark, the final embers of the age of starlight. The last star will not go out dramatically. There will be no final supernova, no grand closing spectacle. A red dwarf, somewhere in what was once a galaxy, will simply consume the last of its hydrogen. Its core will cool. Its light will fade. And the universe will enter a darkness that it has not known since the cosmic dark ages, but this time, there will be no cosmic dawn to follow it. The age of stars will be over. But that moment is so far in the future that from where we stand, in the warm, luminous afternoon of the stelliferous era, surrounded by hundreds of billions of burning suns, it is almost impossible to hold in the mind as anything other than an abstraction. A fact that is true, and distant, and strangely peaceful in its inevitability. The stars are still here. The light is still abundant. And the universe, though it has passed its peak, is still generous beyond all measure with the energy it gives. Of all the stars in the universe, the ones that will matter most in the end are the ones you would least expect. They are not the brilliant blue giants that blaze across young galaxies, burning through their fuel in a few million years and dying in spectacular supernovae visible across billions of light years. They are not sun-like stars, warm and steady, nurturing planetary systems across billions of years of relatively stable output. The stars that will inherit the final chapters of the stelliferous era are small, dim, and almost invisible to the naked eye from any significant distance. They are red dwarfs, and in the long run, they are the dominant form of stellar life in the universe. Red dwarfs are genuinely tiny by stellar standards. The smallest among them have masses as low as about 8% of the mass of the Sun, just barely enough to sustain hydrogen fusion in their cores and qualify as true stars rather than the failed stars we call brown dwarfs. Their surfaces are cool compared to the Sun, around 2,000 to 4,000 degrees Kelvin, which gives them their characteristic deep red color. They emit a fraction of the Sun's light. Some of the dimmest red dwarfs produce only a 10,000th of the Sun's luminosity. If you replaced our Sun with one of the smallest red dwarfs, Earth would be plunged into a cold and perpetual twilight, the sky perhaps lit to a dim reddish glow at noon but never anything like what we know as daylight. And yet, in their smallness lies their extraordinary longevity. The reason stars have limited lifetimes is simple: they are burning through a finite supply of fuel. The faster they burn, the shorter they last. Massive stars are profligate, consuming their hydrogen at extraordinary rates to sustain the fierce nuclear reactions that make them shine so brilliantly. A star 10 times the mass of the Sun might last only 20 million years before exhausting its core hydrogen. The Sun itself will last about 10 billion years in total, of which roughly half has already passed. But a red dwarf burns so slowly, so frugally, that its lifetime extends far beyond anything the current universe has yet experienced. A red dwarf with half the Sun's mass might burn for 50 to 100 billion years. A red dwarf near the lower mass limit, one of those small, dim stars barely massive enough to fuse hydrogen at all, could burn for 10 trillion years or more. That is nearly 1,000 times the current age of the universe. To put that in some perspective, when the last of those small red dwarfs finally exhausts its fuel and fades, the universe will be roughly 1,000 times older than it is today. Every event we know of, the formation of the solar system, the rise of life on Earth, the entire span of human history, every galaxy survey and telescope observation ever conducted, will have occurred in the first thin sliver of cosmic time, less than 0.1% of the way through the stelliferous era as measured from the first stars to the last. We are not near the end of the age of stars. We are near its beginning. Red dwarfs also outlive sun-like stars in a more direct and observable sense. The Sun is already middle-aged. In roughly 5 billion years it will leave the main sequence, expand into a red giant, shed its outer layers, and leave behind a white dwarf. Long after that has happened, long after the Sun has cooled from a white dwarf to a dim orange remnant, and perhaps longer still, the red dwarf stars that exist today will still be burning. They will still be fusing hydrogen in their cores, still maintaining their slow, steady output, still warming whatever planets orbit them in the narrow habitable zones close to their dim surfaces. Red dwarfs are also thought to be fully convective, at least the smallest among them. In the Sun, only the outer layers circulate, the core hydrogen burns in a relatively isolated region, and helium ash accumulates there, eventually triggering the expansion into a red giant. But in a small red dwarf, the entire star mixes. Fresh hydrogen is continuously cycled into the core, and the helium that results is cycled outward. This means a small red dwarf can use nearly all of its hydrogen fuel, not just the portion in its core. It burns more efficiently, more completely, and for far longer as a result. Eventually, though, even the most patient red dwarfs reach their end. As a red dwarf exhausts its hydrogen, what happens next is somewhat different from the fate of sun-like stars, and the details depend on the star's mass. The smallest red dwarfs are not expected to expand into red giants in the way the sun will. They may simply contract and cool, transitioning directly into white dwarfs without passing through a giant phase at all, skipping the dramatic expansion entirely. More massive red dwarfs, closer to the sun's size, may undergo a more sun-like evolution, briefly brightening and expanding before shedding their outer layers. But the destination, for almost all of them, is the same. The last star will not go out in fire. Somewhere in the universe, in the unimaginable depths of future time, the very last red dwarf will exhaust the last of its hydrogen. There will be no supernova, no explosion, no light show ending. The fusion reactions in its core will simply slow and stop. The star will contract. Its light will fade from red to deep infrared to nothing. And the stelliferous era, the age that began with the ignition of the first stars hundreds of millions of years after the Big Bang, and that has defined the character of the universe for virtually its entire luminous history, will be over. No new stars will form to replace it. The raw material for star formation, the cold molecular hydrogen gas that stars require, will long since have been used up, locked into stellar remnants, or dispersed too thinly to gather under gravity. The last star will leave behind a universe that still contains matter, still contains energy in various forms, but no longer contains any source of sustained, self-renewing light. What comes after is the era of dead stars. The name is stark, but it is also, in a way, slightly misleading. Dead stars are not entirely inert. They are not nothing. They are, in their own quiet way, remarkable objects, and the most abundant remnant left behind after the stelliferous era will be white dwarfs. The vast majority of stars, estimates suggest somewhere between 90 and 97% of all stars that will ever exist, will end their lives as white dwarfs. Neutron stars, formed from the collapsed cores of massive stars and supernova explosions, are less common. Black holes, formed from the most massive stars, rarer still. But white dwarfs, the dense remnants of sun-like and smaller stars, will be scattered throughout the remnants of galaxies in enormous numbers. They are, in a sense, the final form of most stellar life. A white dwarf is extraordinary in itself. When the sun eventually sheds its outer layers and leaves behind its core, what remains will be an object roughly the size of the Earth, perhaps slightly larger, but containing the mass of the original stellar core. The density is immense. A teaspoon of white dwarf material would weigh several tons on Earth's surface. The gravity at a white dwarf's surface is roughly 300,000 times stronger than Earth's surface gravity. And they are hot. Newly formed white dwarfs emerge from the planetary nebula phase at surface temperatures of 100,000 degrees or more, far hotter than any living star of similar luminosity, blazing in ultraviolet radiation so intense that they ionize the surrounding nebular gas and cause it to glow. That glowing shell, the planetary nebula, is one of the most visually spectacular phenomena in astronomy. A white dwarf is essentially a naked stellar core, stripped of its outer layers, radiating its stored thermal energy directly into space without any nuclear reactions sustaining it. And that is the key distinction. A white dwarf does not fuse anything. It is not a star in the active sense. It has no nuclear furnace. It shines purely because it is hot, and it cools over time as it radiates that heat away into the surrounding universe. The process is slow, far slower than most people would intuitively expect, because a white dwarf is incredibly dense, and its small surface area relative to its mass limits how quickly it can radiate energy. It is a long, slow exhale. Over billions of years, a white dwarf cools. Its surface temperature drops from the blazing ultraviolet emitting temperatures of youth to the temperatures of a sun-like star, then to something cooler, then to something dimmer. It transitions from white to yellow to orange to red, growing less luminous all the while. The oldest white dwarfs we have yet observed in our galaxy, formed from the first generation of stars, have already cooled to surface temperatures of only a few thousand degrees, far cooler than the sun, dim and reddish and very difficult to detect. But here is something remarkable about the interior of a white dwarf during this long cooling process. As a white dwarf cools, the material in its interior begins to crystallize. A white dwarf is composed primarily of carbon and oxygen, the products of the nuclear reactions that sustain the original star, compressed to extraordinary densities by gravity. At those densities, the atoms are stripped of their electrons, and the material exists as a plasma of nuclei and free electrons. As the white dwarf cools and the thermal energy decreases, there comes a point where the electrical interactions between the carbon and oxygen nuclei become strong enough relative to the thermal energy to organize them into a regular structure. The nuclei settle into a lattice. The interior of the white dwarf becomes, in essence, a crystal. A crystal made of carbon and oxygen, compressed to densities millions of times greater than anything on Earth, spanning an object the size of a planet. There is a famous and entirely accurate way to describe this. Some white dwarfs will, during their cooling, develop interiors that are crystalline carbon under enormous pressure. They are, in the most technically defensible sense, diamond. Planet-sized diamonds, cooling slowly in the dark of space. The universe makes these quietly, without ceremony, from the cores of ordinary stars. This process of crystallization has been confirmed observationally. When astronomers study the cooling rates of white dwarfs in detail, they find that the cooling slows at certain temperature ranges, consistent with the release of latent heat as the interior crystallizes. The crystal transition releases energy, briefly delaying the cooling, and this delay is detectable. We have measured the heartbeat of dying stars slowing as they solidify. But even this slow crystallization, even this long cooling from blazing ultraviolet furnace to crystalline dark cold, takes an enormous amount of time. And here the story arrives at one of the most striking facts in all of the long-term future of the universe. No black dwarf yet exists. A black dwarf is the theoretical final state of a white dwarf, a cooled stellar remnant that has radiated away essentially all of its thermal energy and reached equilibrium with the surrounding universe. An object the size of a planet, made of crystallized carbon and oxygen, cold, dark, carrying no light of any kind, neither fusion-powered nor thermally emitted. Just mass, in space, in the dark. The time required for a white dwarf to cool to the black dwarf stage is estimated at somewhere between 1 quadrillion and 10 quadrillion years. That is between 10 to the power of 15 and 10 to the power of 16 years. The current age of the universe is approximately 13.8 billion years, or about 10 to the power of 10 years. The cooling time required to produce even a single black dwarf is therefore at minimum 100,000 times longer than the universe has currently existed. This means something rather astonishing. In the entire history of the universe, from the Big Bang to this moment, not one black dwarf has yet formed. Every white dwarf that has ever been created, from the first stellar remnants that formed in the earliest galaxies, through every subsequent generation of stars that has since lived and died, is still glowing, still warm, still radiating heat into space. Not one of them has had time to cool to darkness. The universe is old by human standards. 13.8 billion years is a number that strains comprehension. And yet it is not old enough to have produced even a single example of what will one day be the most common object in the universe. The era of dead stars, the age defined by the slow cooling and crystallization of countless white dwarfs into cold, dark remnants, has not yet truly begun. We are, even now, too early. And so the black dwarf remains theoretical. Not in the sense that its existence is uncertain, the physics that predicts it is well understood, and there is no known process that would prevent white dwarfs from eventually cooling to their final dark state. But in the sense that it is a prediction about the future, a projection of known physics forward into timescales so vast that no observation will ever confirm it directly within the lifetime of any civilization. We know it will happen. We simply cannot yet see it happening. There is something quietly philosophical in that. The universe contains within itself the seeds of objects that it has not yet had time to produce. The black dwarfs are already written into the future of every white dwarf burning today, every crystallizing core, every slowly cooling remnant of a sun-like star, is already on the path toward that final darkness. It will simply take longer than the universe has so far existed, perhaps many times longer, before the first one arrives. In the meantime, the white dwarfs cool. Planet-sized crystals of carbon and oxygen, a few tons per teaspoon, scattered through the remnants of dead galaxies, glowing in whatever wavelengths their cooling permits, infrared, then microwave, then effectively nothing. Each one a kind of clock, ticking away in the long dark after the last star has gone out. Each one a record of a star that once burned, that once contributed its light to the stelliferous era, that once was warm. They are the embers of everything. And they are not yet cold. After the last red dwarf fades, after the last white dwarf has radiated the last of its accessible thermal energy into the surrounding void, the universe will enter a darkness more complete than anything that has come before. Not the darkness of the cosmic dark ages, which was a temporary quiet between the release of the cosmic microwave background and the ignition of the first stars. That darkness had a future, gravity was working, gas was gathering, and the cosmic dawn was already written into the physics of the situation. This darkness is different. It has no such future written into it. There are no great reserves of hydrogen waiting to collapse into new stars. The stellar era is finished, and what remains is a universe populated almost entirely by objects that no longer burn, white dwarfs in various stages of cooling, neutron stars spinning slowly in the dark, black holes of various sizes sitting silently at the centers of what were once galaxies, and the cold remnants of planets and moons and all the other debris of the stelliferous era, drifting in expanding space with nowhere particular to go. This is the degenerate era. And on the surface, it seems like a story that has ended. But physics, it turns out, has a few more things to say. The darkness of the degenerate era is not entirely absolute, and the reason has to do with something that has never been directly observed, but that our best theoretical understanding of particle physics strongly predicts. It is one of the stranger ideas in all of science, the idea that the proton, the sturdy fundamental particle at the heart of every atomic nucleus, is not permanent. Protons are, on any human timescale, essentially immortal. The current experimental lower bound on the proton lifetime is around 10 to the power of 34 years. That is an enormous number, incomparably larger than the current age of the universe, larger even than the cooling timescale for white dwarfs to become black dwarfs. No human experiment has ever detected a proton decay. We have built enormous tanks of ultra-pure water deep underground, lined with sensitive detectors, and watched them for years, and never seen a single proton spontaneously decay. The proton is extraordinarily stable. But stable is not the same as eternal. Many extensions of the standard model of particle physics, grand unified theories, supersymmetric models, various other frameworks attempting to unify the fundamental forces, predict that protons should eventually decay. The exact timescale varies depending on the specific theory, but a commonly cited estimate places the proton lifetime at somewhere around 10 to the power of 33 to 10 to the power of 40 years. Far beyond any timescale we have discussed so far, but finite. And in the deep future of the degenerate era, that timescale becomes relevant. When a proton decays, it does not simply vanish. It releases energy. The decay products, which in most proposed decay channels include a positron and a neutral pion, the pion itself quickly decaying into gamma-ray photons, carry with them the energy that was locked into the proton's rest mass. That energy is released as radiation. As light, in the broadest sense. In the deep dark of the degenerate era, proton decay would represent a genuine, if extraordinarily faint, source of illumination. Every black dwarf, every cold neutron star, every rocky planetary remnant drifting through the void would be, over these immense timescales, slowly glowing. Not from any nuclear fire, not from any chemical process, not from any residual heat, but from the decay of the protons in their own atomic nuclei. The matter itself would be radiating, one proton at a time, on timescales that make the current age of the universe look instantaneous. The glow would be imperceptible by any standard we currently use to measure light. The power output of a black dwarf undergoing proton decay would be something like 400 watts, roughly the output of a few incandescent light bulbs, spread across an object the size of a planet. It would be dim beyond all practical description. But it would be real. And in a universe otherwise completely dark, even that faint emission would be the only light anywhere. This is one of the more haunting images that physics offers us of the far future. In the vast darkness after the last stars have gone, the remaining matter in the universe would glow, very faintly, from the inside out, not from energy flowing in, but from the slow disintegration of its own fundamental constituents. The light of dying matter in a universe that has otherwise gone quiet. But proton decay does something even more fundamental than produce a faint glow. It transforms matter. Every proton that decays removes a particle from whatever structure it was part of. A black dwarf is made of crystalline carbon and oxygen, atoms whose nuclei are built from protons and neutrons. As protons decay, those nuclei lose their integrity. The solid crystalline structure of the black dwarf begins to erode at the most fundamental level. And over timescales comparable to the proton lifetime, around 10 to the power of 40 years, the solid objects of the degenerate era would gradually disintegrate. The black dwarf would not explode or shatter. It would simply dissolve, slowly, as the protons in its nuclei decayed one by one, releasing their energy as radiation. The crystalline interior would come apart. The carbon and oxygen would eventually cease to exist as carbon and oxygen in any meaningful sense. What remained would be a diffuse cloud of decay products, positrons, electrons, photons, perhaps neutrinos, drifting outward in all directions. The solid objects of the universe would turn to gas. Not through heat or chemical reactions, but through the fundamental instability of matter itself, operating on timescales beyond anything else we have discussed. There's also a subtle warming effect associated with this process. As protons decay within a white dwarf or black dwarf, the energy they release is deposited within the object, briefly warming it above the temperature it would otherwise have reached through simple cooling. The proton decay heating is tiny, the warming involved is negligible by any conventional standard, but in a universe so cold and so dark that even this faint internal heating matters, it represents a genuine departure from pure cooling. The dying embers of matter would glow a little warmer than simple thermal physics would predict, heated from within by their own dissolution. Long before proton decay completes its work, however, there is another process that deserves attention. It is slower than proton decay but operates on all matter through a different mechanism, and it leads to one of the stranger predicted endpoints in the deep future of the universe. It begins with a simple fact: in any collection of massive objects orbiting a common center, there are quantum mechanical processes, and for very large collections, classical gravitational processes, that can gradually transfer angular momentum outward. Outer objects gain energy and drift to wider orbits, while inner objects lose energy and spiral inward. In a galaxy, this process is dominated by gravitational interactions between stars and stellar remnants, and it operates over timescales of perhaps 10 to the power of 20 years. Over such timescales, the remnants of galaxies would gradually sort themselves, the outer objects drifting away to enormous distances, while the inner remnants spiral slowly inward, eventually gathering at the center of the former galaxy's potential well. And at those centers, most large galaxies already have something waiting. Supermassive black holes. The remnants that spiral inward would eventually be consumed by those central black holes, feeding them incrementally over these vast timescales. But those stellar remnants drifting outward into intergalactic space, the ones that gained angular momentum, would eventually be too loosely bound to the galaxy to remain associated with it. They would drift free, becoming isolated objects in the expanding void. This rearrangement would leave behind, in each former galaxy, a central black hole surrounded by a gradually thinning population of remnants, with much of the original mass dispersed into intergalactic space. But there is another extraordinary endpoint predicted for the remnant matter that remains in denser configurations. Given enough time, timescales of around 10 to the power of 15 years, even the most energetically stable nucleus available to matter under the relevant conditions would become the preferred state. That nucleus is iron. Iron 56 has the lowest binding energy per nucleon of any element, meaning it is the most stable nuclear configuration that ordinary matter can achieve. Over these colossal timescales, through quantum tunneling and nuclear reactions proceeding at rates so slow they make proton decay look rapid, ordinary matter would gradually rearrange itself toward iron. Carbon, oxygen, silicon, the elements that make up white dwarfs and rocky planetary remnants, would slowly, through an almost imperceptible series of nuclear transformations, tend toward the most stable configuration available. The result, if proton decay does not intervene first, would be objects made predominantly of iron. Cold, dark, crystalline iron stars, in the terminology of long-term cosmology. Not stars in any active sense. Not fusing, not burning, not emitting anything significant. Simply iron, in space, at temperatures approaching absolute zero, the final expression of matter's tendency toward its most stable nuclear configuration. Iron stars are perhaps the most peaceful endpoint imaginable for the matter of the universe, cold, stable, silent, waiting patiently in the dark for either proton decay to slowly unmake them or for some other process to disturb their long rest. They are matter at its most settled, its most fundamental stable form, no longer capable of any of the reactions that produced the light and heat of the stelliferous era. In a universe of iron stars, darkness, and slowly evaporating black holes, the story might seem to be essentially over. Not finished, perhaps, but finished with anything interesting. And yet, physics has one more surprise. When astronomers and physicists consider the very long-term future of white dwarfs, and eventually black dwarfs, they encounter a possibility so unexpected that it almost feels like the universe is reluctant to let the lights go out entirely. It requires understanding something about white dwarfs that was not widely appreciated until relatively recently. White dwarfs span a range of masses. The more massive a white dwarf, the smaller its radius, a consequence of the quantum mechanical pressure that supports it against gravity. And there is a maximum mass that a white dwarf can have while still being supported against collapse. This is the Chandrasekhar limit, named after the physicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s. It sits at approximately 1.4 times the mass of the Sun. A white dwarf above this mass cannot be supported by electron degeneracy pressure and will collapse either to a neutron star or, in many cases, triggering a thermonuclear explosion, a type Ia supernova. This is already well understood in the context of the present universe. White dwarfs and binary star systems can accrete matter from a companion, gradually gaining mass until they approach the Chandrasekhar limit and detonate. These supernovae are among the most luminous events in the universe, briefly outshining entire galaxies. But in the deep future, the binary star scenario becomes unavailable. All the companion stars are gone. There is no material to accrete from. The white dwarfs cool to black dwarfs alone, in the dark, with nothing nearby to give them mass. And yet mass can still be added, over time, through another mechanism. In the vast darkness of the degenerate era, black dwarfs will occasionally encounter other objects, other black dwarfs, neutron stars, wandering planetary remnants, through gravitational interactions. Most of these encounters will result in nothing dramatic. But some, over extraordinarily long timescales, will result in actual mergers, or in enough mass transfer to push a black dwarf's mass over the Chandrasekhar limit. And when that happens, when a cold, dark, crystalline remnant of a dead star finally accumulates enough mass to exceed the limit that electron degeneracy pressure can support, it will explode. A black dwarf supernova. In a universe that has been dark for longer than the stelliferous era ever lasted, in a cosmos that has known no new starlight for trillions upon trillions of years, a single point in space will suddenly blaze with thermonuclear fire. Briefly, but genuinely and intensely, brighter than any galaxy once was. A flash of light in a universe that had forgotten what light was. The energy released in such an explosion would be staggering, comparable to a present-day type Ia supernova in total output. For a brief cosmic moment, that explosion would be the only light in the universe. Not a faint glow from proton decay, not the last dim emission of a cooling remnant, but a genuine thermonuclear detonation. An enormous, brilliant, transient flash of fire in an otherwise completely dark and frozen cosmos. The image this produces is one of the most striking in all of long-term cosmology. Picture a universe that has been dark for a duration that makes the current age of the universe look like a single second in a human lifetime. A universe of cold iron stars and crystallized black dwarfs drifting apart in expanding space. No stars, no galaxies, no ongoing nuclear reactions of any kind. And then, somewhere, in some former galaxy, around some former galactic center, among some drifting population of remnants, a collision, or a slow accretion event, pushes a black dwarf past its limit. Fire, in a universe of ice. It is a beautiful and strange thing to contemplate. The universe, in this era, would not be entirely finished with light. It would produce these final transients, these last dramatic events, scattered across the deep future at intervals so infrequent that any given observer would have to wait longer than the current age of the universe between events. But they would happen. Physics demands it, as long as matter capable of undergoing the Chandrasekhar instability remains. These explosions are sometimes called the last interesting transients, a phrase that has a certain melancholy poetry to it. Not the last events, perhaps, but the last events that have the quality of drama. The last moments in cosmic history that produce something we would recognize, in any intuitive sense, as spectacular. After them, the story continues, but it becomes quieter and quieter, dominated by processes so slow and so diffuse that even calling them events seems generous. The universe will have its last fireworks. They will be extraordinary by any measure. And they will be witnessed by no one, in a universe that has long since grown too cold and too sparse for life of any kind to persist. There is something in that image that resists easy categorization. It is not sad, exactly. The universe owes us nothing. It did not create its physics for our benefit or our observation, and its long future after we are gone is not a tragedy. It is simply what happens when you follow the laws of physics forward through time without flinching. And following those laws forward, you find that the universe is remarkably generous with its surprises. That even in the depths of the degenerate era, among cold iron stars and crystallizing remnants in a dark and nearly empty cosmos, the physics of matter continues to produce moments of genuine brilliance. Brief, isolated, impossibly rare, but real. The last lights of the universe will not be stars in any familiar sense. They will be the final detonations of objects that were once stars, long cooled and long dark, pushed past their limits one last time by the slow gravitational choreography of a universe winding toward its end. And when the last of them fades, when the last black dwarf supernova has spent its energy and expanded into a cooling cloud of nuclei and radiation, the universe will settle into something that is very close to its final state. Not yet the dark era. Not yet the absolute end of everything interesting. But close. The embers are almost out. There is a physicist named Matthew Kaplan who has spent time thinking carefully about the very end of the universe, and he arrived at a conclusion that he described with a quiet precision that is worth holding on to. He said that these final explosions, the black dwarf supernovae of the deep future, would be, in his words, the last interesting thing to happen in the universe. Not the last thing. Not the final event in the long ledger of cosmic history. But the last interesting thing. The phrasing carries within it a kind of honesty that pure scientific language sometimes struggles to achieve. It acknowledges that the universe has a quality to its history, that some eras are richer than others, some events more worth noting than others, and that there is a point, far in the future, beyond which the story continues but the narrative has largely resolved. Kaplan's work on black dwarf supernovae is not simply a calculation. It is, in a quiet way, an attempt to find the last chapter of the universe's story that still has something to say. And what it says is stranger and more specific than you might expect. Not every black dwarf will explode. This is a crucial detail, and understanding it requires understanding something about the range of masses that white dwarfs, and therefore black dwarfs, can have. White dwarfs form from the cooling cores of stars that have exhausted their nuclear fuel. The mass of the resulting white dwarf depends on the mass of the original star, but it is always significantly less, because the star loses much of its mass during the red giant phase and the planetary nebula ejection. Stars somewhat more massive than the Sun produce white dwarfs near the upper end of the allowed range. Stars like the Sun, or smaller, produce white dwarfs toward the lower end. The overall distribution of white dwarf masses peaks around 1/2 to 6/10 of the Sun's mass, with the allowed range extending from roughly 17% of the Sun's mass at the low end up to the Chandrasekhar limit of about 1.4 solar masses at the high end. Most white dwarfs, therefore, are well below the Chandrasekhar limit. A white dwarf at half the Sun's mass would need to nearly triple in mass before it became unstable. A white dwarf at 6/10 of the Sun's mass would need to gain almost a full solar mass of additional material. These objects are not on the verge of instability. In the present universe, they are safe. They will never accrete enough material from their surroundings to approach the limit, and so they will never explode. But in the deep future of the degenerate era, the relevant question is not whether a black dwarf can accrete material from a companion. The relevant question is more subtle. It has to do with the internal physics of the black dwarf itself, and with the extraordinary timescales available for processes that are, at any given moment, vanishingly slow. The process that Kaplan identified involves pycnonuclear reactions, nuclear fusion reactions that occur not because of thermal energy, as in living stars, but because of the quantum mechanical phenomenon of tunneling. At the densities present inside a white dwarf or black dwarf, atomic nuclei are packed closely enough that there is a small but non-zero probability, at any given moment, for two neighboring nuclei to tunnel through the energy barrier that normally prevents fusion and fuse together. At ordinary temperatures, this process is negligibly slow, so slow that in the present universe, it effectively does not happen on any relevant timescale. But given enough time, trillions upon trillions upon trillions of years, even tunneling rates this small add up. In a cold black dwarf, pycnonuclear reactions would very slowly convert lighter nuclei into heavier ones. Carbon and oxygen would gradually be transmuted into neon, then magnesium, then silicon, then heavier elements still, working their way up the periodic table through successive fusion reactions driven not by heat but by quantum tunneling and the relentless pressure of the dense interior. And here is where the mass dependence becomes critical. The rate of pycnonuclear reactions depends strongly on the density of the material, and the density of a white dwarf or black dwarf depends on its mass. More massive white dwarfs are smaller and denser. Paradoxically, the more mass you add to a white dwarf, the smaller it gets, because the electron degeneracy pressure that supports it compresses more tightly under greater gravity. A more massive black dwarf has higher interior densities, and therefore faster pycnonuclear reaction rates. Kaplan's calculation showed that black dwarfs above a certain mass threshold, roughly 8/10 of the Sun's mass, would eventually undergo pycnonuclear reactions fast enough to build up a core of increasingly heavy elements, ultimately producing a core of iron or nickel. And once that iron core grows large enough, it collapses. The collapse triggers a thermonuclear runaway in the surrounding layers of lighter elements, a detonation that propagates outward through the black dwarf at close to the speed of sound within the material, releasing the nuclear binding energy of the fusing material in an enormous explosive pulse. A supernova. From a cold, dark, crystalline object that has not produced meaningful light in longer than the current age of the universe. Black dwarfs below this mass threshold, roughly those below 8/10 of a solar mass, will not undergo this process on any relevant timescale. Their interior densities are too low, and their pycnonuclear reaction rates too slow, for the necessary nuclear buildup to occur before some other process, proton decay, most likely, unmakes them first. The lower mass black dwarfs will simply cool and dim and eventually dissolve as their protons decay, without any final explosion. Only the more massive black dwarfs will end in fire. And within the range of black dwarfs that will eventually explode, there is a further subtlety. The timing of the explosion depends on mass. The most massive black dwarfs, those closest to the Chandrasekhar limit, will explode first, because their higher densities drive faster pycnonuclear reactions. Kaplan estimated that the most massive qualifying black dwarfs might explode after roughly 10 to the power of 1,100 years. The less massive ones, near the lower boundary of the exploding range, would take longer, staggeringly longer, perhaps 10 to the power of 32,000 years. These are numbers that have essentially no intuitive meaning. They are not just large. They are large in a way that ruptures the normal operation of the imagination. The difference between 10 to the power of 1,000 and 10 to the power of 32,000 is itself a number larger than anything encountered elsewhere in cosmology. The universe's timeline, from the Big Bang to the present, occupies only the first 10 years of a story whose final chapter arrives 32,000 digits into an exponent. But Kaplan was not content to simply identify that these explosions would occur. He wanted to know how many. This required estimating what fraction of all the stars that will ever exist in the observable universe will produce black dwarfs in the right mass range to eventually explode. And the answer, after careful calculation, is roughly 1%. Only about 1% of all the stars that will ever form are expected to produce black dwarfs massive enough to eventually detonate through pycnonuclear runaway. The other 99% will produce black dwarfs that simply cool and crystallize, and eventually dissolve through proton decay, or drift through the darkness untouched by any dramatic final event. 1% is a small fraction. But 1% of a very large number is still an extraordinary number. And the number of stars that will ever exist in the observable universe is, by any measure, staggering. Current estimates of the total number of stars in the observable universe sit at somewhere around 100 billion trillion. That is 10 to the power of 23. Some estimates go higher. If roughly 1% of those stars will eventually produce exploding black dwarfs, then the number of black dwarf supernovae expected across the entire future history of the observable universe is on the order of 1 billion trillion explosions. 10 to the power of 21 individual thermonuclear detonations, each one briefly the most luminous event in the universe at the moment it occurs. A billion trillion supernovae. Each one separated from the next, in time and space, by intervals so vast that no observer could witness two of them. Each one occurring in a universe so dark and so cold that the explosion itself would be, however briefly, the only light anywhere in the observable cosmos. A solitary flash in an otherwise featureless void, expanding outward into emptiness, cooling and dispersing, fading, and then, darkness again. Kaplan's estimate of the full timeline for these events gives them a window of activity stretching from roughly 10 to the power of 1,000 years to 10 to the power of 32,000 years. The explosions begin, if begin can be used for a process starting a googol times further in the future than the present, with the most massive black dwarfs detonating, and then proceed, at a pace incomprehensibly slow by any standard, through the mass distribution, ending with the least massive qualifying black dwarfs finally igniting after a duration that makes the earlier explosions seem almost recent. And then that window closes. The last qualifying black dwarf detonates. The last flash of thermonuclear fire expands and fades. And the universe contains no more objects capable of producing that kind of event. The era of black dwarf supernovae, if something spread over timescales of 10 to the power of 32,000 years can be called an era, comes to its end. What makes this entire picture particularly remarkable is a fact that sits at the intersection of physics and history. None of this has ever happened before. The universe is approximately 13.8 billion years old. The first black dwarf supernovae are not expected to occur until roughly 10 to the power of 1,100 years from now. The gap between the present and the first of these events is so incomprehensibly large that it cannot be meaningfully expressed in terms of any timescale we normally use. It is not just that black dwarf supernovae have not yet occurred, it is that the universe is so far from the point where they will occur that the comparison barely registers. In the entire history of the cosmos, through the primordial era, through the cosmic dark ages, through the cosmic dawn, through 10 billion years of peak star formation and the long subsequent decline, through the births and deaths of hundreds of billions of stars across hundreds of billions of galaxies, through the formation of every white dwarf that has ever cooled, through every supernova and every merger and every event that has ever lit up the sky, not one black dwarf supernova has occurred. Not even close to occurring. The phenomenon that Kaplan identified is entirely predictive. It exists only as mathematics, as a projection of known physics forward through time into a regime that the universe has not yet entered and will not enter for an unimaginable duration. It is, in the strictest observational sense, a theoretical prediction with no empirical examples, and there is no possibility of ever observing the first one, not from any civilization that could conceivably exist in the near-term future of the universe, not from any instrument we could build, not from any vantage point available to us or to anyone who might come after us within any reasonable span of time. We know it will happen, and we will never see it. There is a phrase that captures the quality of this knowledge rather well. These final explosions have been described as silent fireworks. Not because they will be silent in any physical sense. A thermonuclear supernova is among the most energetic events the universe knows how to produce, releasing more energy in a brief detonation than the sun will emit across its entire 10 billion year lifetime. They will be violent and brilliant, and in energy terms, overwhelming. But they will be silent to the universe in the sense that matters most. There will be no one to hear them. There will be no civilization, no planet, no biology of any kind capable of witnessing them or recording them or finding in them any meaning. The light will travel outward through empty space, redshifting slowly as the universe continues to expand, eventually dropping below any energy threshold that could be called visible. The shock wave will expand into a void so empty that it encounters essentially nothing. The debris will cool and drift. And then the darkness will return, exactly as it was before, except that somewhere in the universe there is now a faintly expanding cloud of cooling nuclear ash where there was previously a cold crystalline remnant of a long-dead star. The fireworks will go off in a universe with no eyes left to see them. This is one of the qualities of the very long-term future that makes it both beautiful and genuinely strange to contemplate. The universe does not require observers to continue operating. It does not simplify its behavior because no one is watching. The pycnonuclear reactions will proceed inside cold black dwarfs according to exactly the same quantum mechanical laws that govern reactions in stellar interiors today, regardless of whether anything capable of detecting them still exists anywhere in the cosmos. The Chandrasekhar instability will be triggered at exactly the threshold it is triggered at today. The detonation will propagate and release energy in exactly the way it always has. The physics is indifferent to the audience. And there is something in that indifference that is, depending on how you hold it in the mind, either cold or strangely comforting. The universe has a story that continues past the last observer. It has a future that does not depend on being witnessed. The laws of physics, written at the beginning of everything, contain within them the description of events that will occur 10 to the power of 32,000 years from now, in conditions so alien that the present cosmos would be unrecognizable, producing light that no eye will ever see. The story does not need a reader to be true. And in those final flashes, in those silent, brilliant, solitary detonations scattered across an almost incomprehensible span of future time, there is something that feels, even across the unbridgeable distance of understanding, like a kind of finale. Not the end of the universe, but the end of the universe's capacity for drama. The last moments when matter, in its final configurations, does something surprising. The last times when the darkness is, however briefly, interrupted. After the last black dwarf supernova fades, the universe will enter a phase from which there is no return to complexity. The black hole era will follow, where even the remnants of remnants have been consumed or dispersed, and what remains are black holes of various sizes slowly evaporating through Hawking radiation over timescales that would make the black dwarf supernova era look brief. And then, beyond even that, the dark era, cold, expanding, empty, with no structures of any significance remaining anywhere in the observable cosmos. But that is a story for another time. For now, it is enough to sit with the image of those last fireworks. 1 billion trillion of them, stretched across a duration of time so vast it has no name. Each one alone in the dark. Each one brilliant, and purposeless, and real. Each one the final act of a star that burned, perhaps, 10 trillion years before, that warmed a planet, perhaps, that lit a sky, that was looked at and named and wondered about, and that eventually cooled to silence, and waited in the dark for its last moment to arrive. The universe will have its ending. And it will be lit, for a while, by the ghosts of stars. In the far future of the degenerate era, the universe will be a place of profound isolation. The galaxies will be gone, not destroyed, but dispersed. Over timescales of around 10 to the power of 20 years, gravitational interactions between the stellar remnants within each former galaxy will have slowly redistributed energy among them, sending some objects inward toward the central black hole and flinging others outward into intergalactic space. The tight, structured collections of stars and gas that we recognize as galaxies today will have dissolved into vast, tenuous halos of black dwarfs and neutron stars and cold planetary remnants, orbiting loosely around massive black holes that have themselves grown quiet. And beyond the boundaries of those former galaxies, in the immensity of intergalactic space, individual black dwarfs will drift alone, launched outward by ancient gravitational interactions, now moving through the void with no companions, no destination, and no prospect of any significant interaction for timescales that dwarf everything we have discussed. These are the isolated stars. Not stars in the burning sense. Stars in the sense of having once been part of the stellar inventory of the universe, now reduced to cold remnants, each one an island in a darkness so complete that the nearest neighbor might be millions of light years away. It is within these isolated objects, these cold, crystalline, planet-sized remnants of dead stars, that the last interesting physics of the material universe will quietly unfold. To understand what will eventually happen inside a black dwarf, it helps to understand what kind of place the interior of a white dwarf actually is. It is not empty space with atoms floating in it. It is matter compressed so thoroughly that normal atomic structure barely applies. The electrons have been stripped from their nuclei entirely, not by heat but by the sheer pressure of the overlying material, and they form a dense sea of free electrons surrounding closely packed atomic nuclei. The nuclei themselves, carbon and oxygen, in the case of a typical white dwarf, are separated from each other by distances far smaller than in ordinary matter, held in their crystalline lattice by the electromagnetic interactions between them. And here is the key physical fact that determines their fate. At these densities, the atomic nuclei are close enough together that quantum mechanics gives each nucleus a small but real probability of tunneling through the energy barrier that normally prevents fusion. In ordinary matter, fusion requires extreme heat to drive nuclei together with enough kinetic energy to overcome their mutual electromagnetic repulsion. But quantum tunneling does not require kinetic energy in the same way. It is a probabilistic phenomenon, a consequence of the wave-like nature of particles at the quantum scale, and it operates regardless of temperature. Even at absolute zero, in a perfectly cold crystal, the tunneling probability is not exactly zero. This process is called pycnonuclear fusion. The prefix comes from the Greek word for dense, which captures exactly what makes it different from ordinary thermonuclear fusion. It is fusion driven by density rather than temperature. In living stars, the fusion reactions that power them are thermonuclear. Temperature is the key variable, and the rate of fusion increases steeply with temperature. In a black dwarf, temperature is essentially irrelevant. The black dwarf is cold. What matters is density, and the quantum mechanical tunneling rate that density enables. The rate of pycnonuclear fusion is extraordinarily sensitive to density, far more sensitive than thermonuclear fusion is to temperature. This is why more massive black dwarfs, which are denser, undergo these reactions so much faster than less massive ones. Even a modest increase in density produces a dramatic increase in the tunneling rate. The most massive black dwarfs, with their highest interior densities, are therefore the first to undergo significant pycnonuclear activity. In practice, the reactions begin with the carbon and oxygen nuclei that make up the bulk of the black dwarf's composition. Two carbon nuclei can tunnel together and fuse, producing heavier elements, neon, sodium, magnesium, depending on the exact channel. Those heavier nuclei can then undergo further reactions, producing still heavier elements. And so on, step by step, the composition of the black dwarf's interior shifts progressively toward heavier nuclei as the eons pass. Each step in this chain releases a small amount of energy, the energy difference between the binding energies of the reactant and product nuclei. That energy contributes to the very faint warming effect we discussed earlier, the pycnonuclear heating that keeps a black dwarf slightly warmer than simple cooling would predict. But the energy release per reaction is small, and the reactions are slow, and the heating is minimal. For most of the black dwarf's long wait, this process is barely detectable by any outside measure. But the composition is changing. Very slowly, over timescales measured in exponents that have no common name, the interior of the black dwarf becomes progressively enriched in heavier elements. The light nuclei are consumed, and the product nuclei accumulate. The critical intermediate product in this chain is nickel-56. It is not the final destination. Nickel-56 is radioactively unstable, but it is a key waypoint in the nuclear pathway that leads toward the eventual runaway. In the present universe, nickel-56 is produced in large quantities by type Ia supernovae, and its subsequent radioactive decay chain is what powers the light curve of a supernova explosion, the weeks-long brightening and fading that makes these events useful as standard candles for measuring cosmic distances. Nickel-56 decays to cobalt-56, and cobalt-56 decays to iron-56. Each step releases energy in the form of gamma rays and positrons. And iron-56, the final product of this chain, is the most stable nucleus that ordinary matter can achieve, the lowest point on the curve of nuclear binding energy. It neither fissions to release energy nor fuses to release energy. It simply sits, stable, at the bottom of the energy landscape. In a black dwarf undergoing pycnonuclear reactions, the gradual buildup of heavier elements eventually leads to an accumulation of iron group nuclei in the core. As this iron core grows, it changes the fundamental character of the material in a way that has profound consequences for the structural stability of the entire object. The stability of a white dwarf and a black dwarf against gravitational collapse depends on the pressure provided by its free electrons. This electron degeneracy pressure is what holds the object up against the enormous inward pull of its own gravity. And electron degeneracy pressure depends, critically, on the number of free electrons available. More electrons means more pressure. Fewer electrons means less. This is where the concept of electron fraction becomes important. The electron fraction is simply the ratio of electrons to total nuclear particles, protons and neutrons combined, in the material. For a white dwarf made primarily of carbon and oxygen, the electron fraction is exactly 1/2, because carbon and oxygen both have equal numbers of protons and neutrons. 1 electron per nucleon, divided equally. This gives a high electron fraction, and therefore strong electron degeneracy pressure, and therefore robust support against collapse. But as pycnonuclear reactions build heavier elements, and particularly as the nickel-cobalt-iron decay chain proceeds, something changes. The heavier nuclei produced in these reactions, and especially the products of the decay chain, tend to have more neutrons than protons. When nickel-56 decays to cobalt-56 and then to iron-56, the process involves positron emission. The nucleus emits a positron, the antimatter partner of the electron, in order to convert a proton into a neutron. Each positron emission reduces the number of protons in the nucleus by 1, and since the number of electrons in the material must balance the number of protons to maintain charge neutrality, each positron emission also reduces the number of free electrons. The electron fraction declines. As the iron core grows and the decay chain operates, the number of free electrons available to provide degeneracy pressure slowly decreases. The support that was holding the black dwarf up against gravity quietly weakens, nuclei by nuclei, positron by positron, over timescales measured in those enormous exponents. And as the electron fraction falls, the threshold mass at which electron degeneracy pressure can no longer support the object against collapse, the effective Chandrasekhar limit for the material, also falls. The black dwarf does not need to gain mass from outside to become unstable. It becomes unstable from within, as its own internal composition evolves toward a state where its existing mass exceeds what the remaining electron pressure can support. When that threshold is crossed, the iron core collapses. The collapse is rapid by any standard, occurring in a fraction of a second once it begins. And as the core collapses, it compresses and heats the surrounding layers of lighter, unburned nuclear material. That heating drives the lighter nuclei across the threshold for rapid fusion. The pycnonuclear reactions that had been proceeding glacially over unimaginable timescales are replaced, in an instant, by thermonuclear reactions running at full speed, powered now by the heat of the collapsing core rather than by quantum tunneling. A fusion flame ignites and propagates outward through the black dwarf at close to the local sound speed. In this dense material, that is a significant fraction of the speed of light. Layer after layer of unburned material is swept up and consumed in the expanding detonation front, releasing nuclear binding energy in enormous quantities as lighter elements are fused into heavier ones all the way up toward the iron peak. The energy released is more than sufficient to unbind the entire star. Unlike a core collapse supernova, where much of the energy goes into the collapsed remnant and the surrounding infalling material, this is a complete thermonuclear disruption. Nothing survives the explosion intact. The entire black dwarf, which has waited in cold darkness for an incomprehensible span of time, is consumed in a matter of seconds. This is the runaway fusion event, the thermonuclear explosion of a black dwarf, and it is the physical mechanism behind what Kaplan identified as the last interesting events in the history of the universe. Now consider what this explosion actually looks like, and what powers the light it produces. In the present universe, when a type Ia supernova occurs, astronomers observe a characteristic light curve, a rise to peak brightness over roughly 2 to 3 weeks, followed by a slower decline over months and years. This light curve is not powered directly by the explosion itself. The initial detonation releases most of its energy as kinetic energy, the outward blast of expanding nuclear ash, and as hard radiation that is quickly trapped and thermalized within the dense expanding ejecta. What actually powers the extended light emission that we observe is the radioactive decay of nickel-56 produced in the explosion. A typical Type Ia supernova produces around half a solar mass of nickel-56, an enormous quantity of an unstable nucleus. That nickel decays to cobalt-56 with a half-life of about 6 days, and the cobalt decays to stable iron-56 with a half-life of about 77 days. Each decay releases gamma rays, and those gamma rays are absorbed by the expanding ejecta and re-emitted as optical and infrared light. The nickel and cobalt decay chain is, quite precisely, the engine that powers the visible light of a supernova for weeks and months after the explosion itself. In a black dwarf supernova, the same mechanism operates. The explosion produces nickel-56, and that nickel drives the light curve through its decay chain. The gamma rays released as the nickel decays to cobalt and then to iron are the ultimate source of the photons that make the explosion visible, or would make it visible, if there were anyone to see it. There is a deep irony in this chain that is worth noting. The decay chain that powers the last light of the last supernova in the universe, the very final act of luminosity associated with ordinary matter, passes through iron, the most stable nucleus. The endpoint of stellar nucleosynthesis, the material that accumulates in the dying cores of massive stars until they can no longer hold back gravity, the element that defines the end of nuclear burning. Iron is both the reason the explosion happened, the buildup of an iron core that collapsed and triggered the runaway, and the final product of the radioactive decay that powers its light. The explosion is, in a sense, caused by iron and lit by iron, a nuclear cycle completing itself in the last fire that ordinary matter will ever make. The light from these explosions will travel outward into an empty universe, redshifting as it goes, growing dimmer with distance and with the expansion of space. In the present universe, supernovae can be detected across billions of light years. But in the deep future, when these black dwarf detonations occur, the universe will be vastly larger than it is today, expanded to perhaps unimaginable scales, and the density of matter will be correspondingly lower. The ejecta will expand into a void so dilute that it encounters essentially nothing. But the gamma rays and the optical photons produced by the nickel decay chain will still travel at the speed of light. They will still carry energy. They will still illuminate, however briefly and however faintly at any given distance, the surrounding darkness. A photon is a photon, regardless of the era in which it is produced, and these photons will be as real as any that have ever traveled through the universe. They will simply have no destination that matters. No detector, no eye, no atom in an excited state waiting to absorb them for any useful purpose. They will travel outward in redshift and cool and eventually become part of the diffused background radiation of a universe that has long since lost any other feature worth noting. And then they will fade. The explosion will last, in terms of its observable light, perhaps weeks or months, the same timescale as present-day supernovae, governed by the same radioactive half-lives, indifferent to the era in which it occurs. The nickel-56 will decay to cobalt on its 6-day schedule. The cobalt will decay to iron on its 77-day schedule. The light curve will rise, and peak, and fall, as it always has. In a universe 10 to the power of 1,000 years old, a 6-day half-life is an inconceivably brief interval. And yet the physics will proceed at exactly that rate. The nucleus does not know what era it is in. It decays according to its own internal quantum mechanical clock, and that clock has not changed since the early universe. There is something almost tender in that constancy. The same decay chains that power supernovae in the present universe, the same physical processes that astronomers have measured and modeled and used to map the expansion of the cosmos, will power the last light that ordinary matter ever produces. The physics of the end is the same physics as the beginning. The universe does not learn new laws as it ages. It simply applies the old ones to increasingly sparse and unusual circumstances, until at last there are no more circumstances left to apply them to. The last supernova will be, in its physics, perfectly ordinary. Unremarkable, even, by the standards of supernovae. The explosion will proceed exactly as the models predict. The nickel will decay. The gamma rays will thermalize. The light curve will follow its familiar shape. It will simply occur in a universe that has forgotten, entirely, what light was for. Every supernova, in the present universe or in the deep future, is in some sense a nickel factory. The thermonuclear detonation that tears through a white dwarf, or, in the far future, a black dwarf, does not simply release energy and scatter the original material outward unchanged. It transforms it. The fusion reactions that propagate through the exploding star are nucleosynthetic events, building new elements from old ones at an extraordinary rate, driven by the energy of the detonation itself. And the primary product of this nuclear transformation, in the heart of the explosion where temperatures and densities are highest, is nickel-56. The quantity produced depends on the mass and composition of the exploding object and the details of how the detonation propagates. A typical present-day type Ia supernova produces somewhere between a few tenths and about 1 solar mass of nickel-56. That nickel is distributed throughout the expanding ejecta, and as the ejecta expands and the gamma rays from the nickel decay chain diffuse outward through the thinning material, the supernova brightens to its peak and then fades over the subsequent weeks and months. In a black dwarf supernova of the deep future, the nickel production would proceed through the same physical mechanism, driven by the same nuclear physics. The exact yield would depend on the mass of the exploding black dwarf and the characteristics of the detonation, but it would be comparable to present-day type Ia supernovae. The explosion would be recognizable, in its energy output and spectral evolution, as belonging to the same class of event, the same basic physics, the same radioactive engine, the same light curve shape. The expanding ejecta from these future explosions would move outward at velocities comparable to those seen in present-day supernovae, typically 10,000 to 30,000 kilometers per second, or roughly 3 to 10% of the speed of light. At those velocities, the ejected material would expand rapidly into the surrounding void. Within days, the ejecta shell would be millions of kilometers across. Within years, it would span light years. Within thousands of years, it would have thinned to the point where it merges imperceptibly with the surrounding interstellar, or rather, by this era, intergalactic, medium. The blast wave would encounter essentially nothing. In the present universe, supernova remnants expand into interstellar gas and dust, sweeping up material and producing the beautiful, glowing nebulae that we observe across the Milky Way, the Crab Nebula, Cassiopeia A, the Veil Nebula. These structures form because there is something for the blast wave to run into. In the deep future, the void surrounding each isolated black dwarf will be so thoroughly emptied that there is no medium to sweep up, no gas to ionize and set glowing, no material to shape into the characteristic shell structure of a supernova remnant. The ejecta will simply expand outward forever, thinning and cooling, leaving no visible structure behind. The two types of black dwarf supernova that Kaplan's work describes are worth distinguishing, because they represent somewhat different physical scenarios even though both result in complete thermonuclear disruption. The first type involves black dwarfs that are already close to the upper end of the allowed mass range, those whose internal pycnonuclear reactions proceed rapidly enough, given their high densities, to build up an iron core and trigger collapse on timescales measured in the lower range of those enormous exponents. These objects undergo the most straightforward version of the process. Density-driven pycnonuclear fusion builds iron in the core, the electron fraction declines through the positron emission of the decay chain, the effective Chandrasekhar limit drops below the object's actual mass, and the core collapses, triggering the thermonuclear runaway. The second type involves slightly less massive black dwarfs, where the process is slower and the pathway somewhat different in its details, but the endpoint is similar, a thermonuclear disruption of the entire object, powered by the same nuclear physics and producing the same class of explosion. The timing differs enormously between these two types, with the less massive ones waiting far longer before their internal composition evolution brings them to the threshold of instability. But both types end in the same fundamental event, complete thermonuclear disruption, a brief flash of light, and the scattering of the remnant into the void. Together, these two populations define the full span of the black dwarf supernova era, the long countdown from the first explosion to the last. And that countdown begins at a moment so far in the future that describing it requires a different relationship with numbers than ordinary experience provides. The first black dwarf supernova is expected to occur at approximately 10 to the power of 1,100 years from now. Written as a number, that would be a 1 followed by 1,100 zeros, a number that fills more than a page if you write it out in standard notation. It has no common name. There is no SI prefix that reaches it. The googol, which is 10 to the power of 100, is itself a number of almost no practical use in any calculation about the real universe, and the timing of the first black dwarf supernova exceeds even that by a factor of 10 to the power of 1,000. The black dwarf responsible for this first explosion will be among the most massive that exist, close to the Chandrasekhar limit, perhaps around 1.3 or 1.4 solar masses. Its high mass means high interior density, and high interior density means relatively rapid pycnonuclear reactions, and relatively rapid reactions mean that it reaches the instability threshold sooner than any of its less massive counterparts. It is the first to go not because of any external trigger, not because of any collision or interaction, but simply because its internal physics has been advancing faster than everyone else's since the moment it formed. By the standards of the other black dwarfs, it is an early finisher. To appreciate the density of these objects and why it matters so much, it helps to compare them to something familiar in a different context. The interior density of a massive white dwarf, and by extension, a massive black dwarf, is comparable to, and in some regions exceeds, the density found in atomic nuclei themselves. We are not talking about material that is merely dense in the way that lead or osmium is dense. We are talking about material compressed to the point where the distinction between the interior of an atom and the space between atoms has largely ceased to be meaningful. The nuclei are not separated by electron clouds and empty space in the usual sense. They are packed together at separations measured in femtometers, the scale of nuclear physics. It is at this scale, under these conditions, that pycnonuclear tunneling operates. And it is the comparison to uranium, one of the heaviest naturally occurring elements, with its own complex nuclear physics and its own tunneling-related decay processes, that sometimes helps calibrate intuition about what is happening inside these objects. Uranium nuclei undergo alpha decay through quantum tunneling, with half-lives measured in billions of years. The pycnonuclear reactions in a black dwarf operate through a similar tunneling mechanism but under conditions of such extreme density that the relevant timescales, while still enormous by everyday standards, are finite and calculable. The black dwarf is not infinitely stable. It has a clock. That clock simply runs at a pace that makes geological time seem frantic. There is another aspect of the deep future that bears directly on these explosions, and it is one of the more quietly melancholy facts in all of long-term cosmology. Even if, by some extraordinary means, an observer existed at the time of these explosions and possessed instruments of perfect sensitivity, they would be unable to see most of them. The reason is the cosmological horizon. In our accelerating universe, objects beyond a certain distance are receding from us faster than light can cross the intervening space. Those objects are, in the most rigorous physical sense, outside our observable universe. We cannot receive signals from them. We cannot detect them. They are as causally disconnected from us as if they existed in an entirely separate cosmos. In the present universe, the observable universe extends to a radius of about 46 billion light-years. But that boundary is not fixed. As the universe expands and the expansion accelerates, more and more of the universe crosses beyond our horizon. In roughly 100 billion years, which is less than 10 times the current age of the universe, and a blink of an eye compared to the timescales of black dwarf supernovae, essentially all galaxies outside our local group will have receded beyond the point where their light can reach us. The observable universe, for any future inhabitants of a local group remnant, will shrink to just the contents of the merged Milky Way Andromeda system and its small satellite galaxies. Everything beyond that will be, in terms of light travel and causality, simply gone from any possible observation. By the time the first black dwarf supernova occurs, the universe will be so vastly expanded that the overwhelming majority of the black dwarfs that will eventually explode will be far beyond any conceivable horizon. The explosions will occur, one by one, in regions of space that are causally disconnected from every other region, There will be no possible observer who can witness more than an infinitesimal fraction of them, if any observer exists at all, which seems overwhelmingly unlikely given the conditions of that era. The countdown, in other words, is a countdown that nothing will be counting. 100 billion years from now, again, a comparatively near-term milestone, the universe will already feel emptied of the richness we know. The galaxies will be receding, unreachable. The cosmic web of filaments and clusters will be dissolving into an increasingly uniform and featureless distribution of matter. The sky, for any hypothetical observer, will be growing emptier as the centuries accumulate. And yet, from the perspective of the black dwarf supernova timeline, 100 billion years is essentially the present. The countdown has barely started. The explosions will come. Slowly, sparsely, one by one across an expanding cosmos, each one alone in its darkness. And after the first, after that most massive, most impatient black dwarf finally reaches its threshold and detonates in the deep future, the countdown continues, moving through progressively less massive objects on progressively longer timescales. Until, at last, it reaches the end. The last exploding black dwarf. Kaplan's calculation identifies this final object with a specificity that feels almost intimate given the cosmic scale of the story. The last black dwarf to detonate through pycnonuclear runaway will have a mass of approximately 1.16 times the mass of the Sun. 1.16 solar masses. Not 1.15. Not 1.2. The precision reflects the underlying physics, the relationship between mass, density, pycnonuclear reaction rate, and the timescale to instability is a continuous function, and the least massive object that still qualifies for eventual detonation sits at a specific point on that curve. Below 1.16 solar masses, the interior density is not quite high enough, the tunneling rate's not quite fast enough, to drive the necessary nuclear evolution within any timescale shorter than the proton decay era, which would unmake the object through a different mechanism before pycnonuclear runaway could complete its work. At 1.16 solar masses, the density just barely crosses the threshold. The reactions proceed, with extraordinary slowness, and after a duration measured by that exponent of 32,000, the iron core grows, the electron fraction falls, the effective Chandrasekhar limit drops below the object's mass, and the last thermonuclear explosion in the history of the universe ignites. It is a modest object, by the standards of the present universe. 1.16 solar masses. A white dwarf of that mass, forming today, would be an ordinary stellar remnant, cooler and denser than average, but unremarkable. It would cool over billions of years, crystallize, transition through the color sequence from white to yellow to red, and eventually become a black dwarf indistinguishable from any other cold remnant of its kind. And then it would wait. It would wait while the stelliferous era ended and the last red dwarfs faded. It would wait while the other black dwarfs exploded, one by one, starting with the most massive and working slowly down through the mass range. It would wait while the black hole era advanced and the great supermassive black holes at the centers of former galaxies slowly evaporated through Hawking radiation. It would wait through durations that have no name, in a darkness that has no analogy. And then the pycnonuclear reactions in its interior, proceeding at their density-limited rate, would finally do what they were always going to do. The composition would shift. The iron core would grow. The electron fraction would fall. And the threshold would be crossed. The last light in the universe, the last light produced by the thermonuclear fusion of ordinary matter, the last photon emitted by any process connected to the stellar history of the cosmos, would come from the explosion of this 1.16 solar mass remnant, in a universe 10 to the power of 32,000 years old, surrounded by emptiness so complete that the word emptiness itself seems inadequate. There is a quality to this image that is difficult to place, emotionally or philosophically. It is not tragic, exactly, nothing is being lost in the moment of the explosion that was not already gone long before. It is not triumphant, there is no one for whom it is a triumph, no narrative that it concludes for any observer. It is simply the last consequence of a chain of physical processes set in motion at the Big Bang, running forward through time according to laws that do not change and do not care, arriving finally at their ultimate output. One explosion. One flash of gamma rays and optical light, powered by the decay of nickel to cobalt to iron. One expanding shell of nuclear ash, moving outward at a few percent of the speed of light into a void that stretches, in every direction, to a horizon that contains nothing. And then the light fades. The nickel is spent. The cobalt decays to iron. The ejecta cools. The last photons redshift into the microwave background of a universe so cold and so expanded that even that background has become vanishingly faint. Silence. Not the silence of the cosmic dark ages, which was pregnant with the future, full of gravity doing its patient work, full of cold hydrogen waiting to collapse, full of the unlit potential of the cosmic dawn. This silence is different in character. It is the silence of completion. Of a story that has reached its last sentence, not because anything interrupted it, but because it said everything it had to say. The universe began with light, with the blazing, incomprehensible energy of the first fraction of the first second, with the billion-degree plasma of the early cosmos, with the release of the cosmic microwave background as the fog cleared and photons traveled freely for the first time. It progressed through darkness into the cosmic dawn, through the peak of star formation at cosmic noon, through the long golden afternoon of the stelliferous era. It dimmed, gradually, through the degenerate era, lit only by the faint glow of cooling white dwarfs and the even fainter warmth of proton decay. It produced its last dramatic events in the scattered, solitary detonations of cold crystalline remnants pushed past their limits by the slow drift of internal physics. And then, with one final explosion from one final object, it used the last of its ordinary matter to make one last flash of light. The number attached to that moment, 10 to the power of 32,000 years, is not a number that can be held in the mind. It is a symbol, a representation, a way of pointing at a duration so remote from present experience that the gap between it and now is itself beyond all comprehension. But the physics that predicts it is real and careful, and the product of our best understanding of how matter behaves at extremes we will never directly observe. We know this will happen. We have calculated when. We have even identified the mass of the star responsible. 1.16 solar masses. Somewhere in the universe, that star already exists. Right now, in some galaxy, orbiting some star that has not yet died, or perhaps already cooling as a white dwarf in a system whose sun has already exhausted its fuel, an object that will one day be the last source of light in the universe is already present in the cosmos, going about the ordinary business of being a stellar remnant. It does not know what it is. It has no knowledge, no purpose, no awareness of the role that physics has assigned it. It is simply matter, following the laws it was given. But one day, in a future so remote that the word future itself becomes strained and strange, it will fulfill what those laws require of it. It will compress, and ignite, and burn, and scatter. And the universe will go dark. The number that marks the end of ordinary light in the universe is not a number in any conventional sense. It is 10 to the power of 32,000. Written out in full, it would require 32,000 digits, 32,000 zeros following a 1, to express. If you were to write it out by hand, 1 digit per second without stopping, it would take nearly 9 hours just to finish writing the number. If you printed it in a standard font on standard paper, it would fill roughly 16 pages. And yet the number itself, that 32,000 digit figure, represents only the exponent. The actual quantity it describes is incomparably larger than the number of digits suggests. There is no word for it. Not in mathematics, not in physics, not in any human language. The universe has produced numbers in its history that strain comprehension: the number of atoms in the observable universe, the number of photons ever produced by stars, the number of Planck times in the current age of the cosmos. All of those numbers, stacked and multiplied together in every possible combination, would not approach what 10 to the power of 32,000 represents. It is a quantity that exists only as a formal symbol, a piece of mathematical notation pointing at something the human mind was not built to hold. And yet it is a real prediction, derived from real physics, about a real event that will occur in the real universe. At 10 to the power of 32,000 years, the last black dwarf will explode. What creates this moment, what drives it, what makes it inevitable, is not a collision, not an external disturbance, not any dramatic intervention from outside. It is the internal logic of quantum mechanics operating inside a cold, crystalline, planet-sized remnant of a star that burned and died in circumstances so ancient that no record of them could possibly survive. The pycnonuclear reactions that produce this final explosion are simply quantum tunneling, proceeding at the rate that the density of the material and the masses of the nuclei allow. Carbon and oxygen nuclei, held in their crystalline lattice, occasionally tunneling through the barrier that separates them and fusing into heavier elements. The buildup of iron. The decline of the electron fraction. The softening of the degeneracy pressure. The collapse of the core. These are not exotic or mysterious processes. They are the same quantum mechanics, the same nuclear physics, the same gravitational dynamics that operate in every white dwarf, every supernova, every stellar core in the present universe. The deep future does not require new laws. It only requires the existing ones to keep running, past every timescale we have names for, until they exhaust the last configuration of matter that they can act upon in any interesting way. The explosion itself, when it occurs, will be physically identical in its essentials to a Type Ia supernova happening in the present universe. The detonation will propagate through the black dwarf in seconds. The ejected material will move outward at tens of thousands of kilometers per second. The nickel-56 will be produced and will begin its decay chain. Gamma rays will thermalize within the ejecta. The light curve will rise over days and weeks, powered by the cobalt decay, and then fall over subsequent months as the radioactive fuel is spent. The photons released will be real photons, indistinguishable in their individual properties from photons produced in any other supernova. They will travel at the speed of light. They will carry energy. They will redshift as they move through expanding space. And there will be nothing to receive them. After the last supernova, the universe enters a phase that is genuinely unlike anything that has come before, not in the dramatic sense of the early universe's transitions, not with the weight of transformation, but with the quiet finality of completion. What remains is a cosmos in which the era of ordinary matter as a source of light is definitively over. The black holes that remain, some of modest stellar mass, others supermassive, descendants of the great central engines of former galaxies, continue their own long process of evaporation through Hawking radiation. That is a story with its own timescales, its own endpoint. But for ordinary matter, for the atoms and nuclei and electrons that make up everything we have ever touched or seen or built, the story of producing light ends with that last explosion. And yet, for a while, for an almost inconceivably brief while, measured against the timescales we have been discussing, the universe still contains one more remarkable kind of structure. After all the matter in the universe has either been consumed in explosions, locked into black holes, or dispersed as the decay products of proton decay, what remains of ordinary matter will be predominantly electrons and positrons. The electrons are the stable negatively charged particles that once orbited atomic nuclei in every atom of every star and planet and living thing that ever existed. The positrons are their antimatter partners, identical in mass but opposite in charge, produced in enormous quantities by the proton decay process, each one a byproduct of a proton's final transformation. In the cold, dark, expanding universe of that era, these particles will be moving slowly, their thermal energy nearly exhausted. And occasionally, an electron and a positron will encounter each other. Under ordinary circumstances, when a particle meets its antiparticle, annihilation follows almost immediately. The two particles destroy each other and release their combined rest mass energy as gamma-ray photons. But the encounter does not always end instantly. Under the right conditions, an electron and a positron can enter a brief, fragile orbit around each other, held together by their mutual electromagnetic attraction, forming a transient atom-like structure before they finally annihilate. This structure is called positronium. It is one of the stranger objects in physics, an atom made entirely of antimatter and matter in equal measure, with no nucleus at all. The electron and the positron orbit their common center of mass in configurations that mirror the electron orbitals of ordinary hydrogen, but with both particles playing equivalent roles. It is hydrogen's antimatter echo, unstable from the moment of its formation, existing only as a countdown to annihilation. The lifetime of positronium depends on which quantum state it forms in. In its simplest singlet state, where the spins of the electron and positron are aligned oppositely, positronium annihilates in less than a nanosecond, releasing 2 gamma-ray photons traveling in opposite directions. In its triplet state, where the spins are aligned in the same direction, the lifetime extends to roughly 142 nanoseconds before annihilation releases 3 gamma-ray photons. 142 nanoseconds. Less than a millionth of a second. In a universe measured in exponents of 10 to the power of thousands, positronium exists for a duration that is, by any relative measure, instantaneous. And yet it exists. It forms. It orbits. It annihilates. It produces gamma rays, real, physical photons, in the process. In the deep future of the universe, the formation and annihilation of positronium atoms will represent one of the last occasions on which the word atom can be meaningfully applied to anything, and one of the last occasions on which matter produces light through a process that is not purely thermal. The gamma rays from positronium annihilation will be the last structured emission from ordinary matter, the final photons produced by a recognizable physical process involving particles in a defined quantum state, rather than simply the thermal glow of a cooling object. They will travel outward into the void, redshift, cool, and join the background radiation of a universe that is, by this point, almost entirely radiation and black holes and the slowly evaporating remnants of structure. There is a caveat to this entire picture, and it is one that determines how much of this final story actually plays out as described. It concerns proton decay. The timeline of positronium formation and the dispersal of electrons and positrons into the late universe depends critically on whether proton decay occurs on the timescale that grand unified theories predict, around 10 to the power of 33 to 40 years, or whether protons are, in fact, stable indefinitely. If protons do decay on that timescale, then by the time the black dwarf supernovae are occurring, at timescales starting around 10 to the power of 1,000 years, proton decay will have already been operating for an unimaginably long time, gradually dismantling all the matter that does not get consumed in explosions. The electrons and positrons released by proton decay would be present throughout the degenerate era and beyond, forming positronium atoms and annihilating as described. But if protons do not decay, if they are stable, as some theories allow, then the electrons that currently orbit atomic nuclei in white dwarfs and black dwarfs would remain locked into those nuclei, unable to roam freely and form positronium. The dispersal of matter into free electrons and positrons would not occur in the same way, and the positronium era, such as it is, would be diminished or absent. We do not currently know whether protons decay. The experimental lower limit on the proton lifetime is extraordinarily long, longer than the current age of the universe by many orders of magnitude, but it does not exclude proton decay on the theoretically predicted timescales. The experiments that would confirm or rule out proton decay at those timescales are simply beyond our current technological reach. It is one of the genuinely open questions in fundamental physics, and its answer shapes the long-term future of matter in ways that no other question quite matches. For the purposes of imagining the deep future, the existence of proton decay is the more interesting scenario, and the more commonly discussed one in long-term cosmology, because it provides matter with a finite and complete life cycle, from the synthesis of protons in the early universe to their eventual decay into lighter particles in the deep future. But the uncertainty is real, and honest accounts of the far future must acknowledge it. By the era of positronium, in any case, there are no observers. This has been true for a very long time before this point, longer, almost certainly, than life of any kind has ever existed anywhere in the universe. The conditions that allow for biology, liquid water, chemical complexity, energy gradients, stable environments operating at temperatures compatible with molecular bonds, disappear long before the degenerate era. The Sun will become uninhabitable for Earth within roughly 1 billion years. Complex life, if it survives at all by moving to different environments, cannot persist indefinitely in a universe that is cooling and dimming and losing its star-forming capacity. The last conceivable niches for life of any kind would close somewhere in the very early stages of the degenerate era at the absolute latest, and that era itself begins so far beyond any conceivable biological timescale that the comparison is barely meaningful. The universe's final acts, the black dwarf supernovae, the positronium atoms, the slow evaporation of the last black holes, occur in a cosmos that has been lifeless for longer than it was ever inhabited. The story does not end with anyone watching. It ends the way it mostly proceeded, quietly, according to physics, without witness. There is no tragedy in this, or at least there need not be. The universe was not made for observers, and its continuation without them is not a failure or a loss. It is simply what happens when the laws of physics are applied to matter and energy over very long timescales. The laws do not require an audience. They do not simplify their behavior when no one is watching. They simply continue. And what they continue toward, after the last positronium atom has annihilated and the last photon from ordinary matter has been released, is something that cosmologists call the Dark Era, the final epoch of the universe, in which nothing remains but black holes slowly evaporating through Hawking radiation, and eventually, after even those are gone, a universe of pure radiation and fundamental particles at a temperature indistinguishable from absolute zero, expanding forever into a darkness that has no bottom and no end. Before arriving at that final scene, it is worth pausing to take in the full sweep of the timescales involved, because the human mind, shaped by evolution for a world of seasons and lifetimes, genuinely struggles with the range of numbers that the universe's story requires. The current age of the universe is approximately 13.8 billion years. That already exceeds easy comprehension. 1 billion years is longer than the history of complex life on Earth, and 13 billion of them is more time than most people have any intuitive purchase on. And yet 13.8 billion years is a vanishingly small quantity compared to the timescales of the universe's future. The Sun's remaining lifetime, roughly 5 billion years, is more than a third of the current age of the universe. Red dwarf lifetimes reach into the tens of trillions of years. The cooling of white dwarfs to black dwarfs takes a minimum of 1 quadrillion years. The black dwarf supernova era stretches from 10 to the power of 1,100 years to 10 to the power of 32,000 years. Each step in this progression does not merely add to the previous timescale, it multiplies it, overwhelms it, makes it irrelevant. The full timeline of the universe is not a line on which the present sits somewhere in the middle. It is a line on which the present sits so close to the beginning that the beginning and the present are, for practical purposes, the same point. We are not in the middle of the universe's story. We are in its opening moments. In the observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is itself a remarkable thing to consider in this context. It currently extends roughly 46 billion light-years in every direction, a sphere of space containing an estimated 2 trillion galaxies, each containing hundreds of billions of stars, a total of perhaps 1 to 2 times 10 to the power of 23 individual stars. That is the universe as we can currently observe it. But the observable universe is not the whole universe. It is simply the portion that is causally connected to us, the region from which light has had time to arrive. The full universe, if it is finite, may be vastly larger. Some inflationary cosmological models suggest it is so much larger than the observable portion that comparing the two is like comparing a single atom to the observable universe itself. If the universe is infinite, as some models allow, then the observable universe is an infinitely small fraction of the whole. As the universe expands and the cosmological horizon evolves, the observable universe as seen from any given point shrinks over time in terms of the number of objects within it. Galaxies cross the horizon and become unreachable. The sphere of causal contact contracts. An observer in the far future, in the unlikely event that any observer exists, would inhabit an observable universe containing, perhaps, only the remnants of their own gravitationally bound cluster, surrounded by a void whose contents have receded beyond any possible detection. And in that shrinking, dimming, cooling observable universe, the final acts of ordinary matter would play out, unseen, unrecorded, but physically real. The last supernova would blaze and fade. The last positronium atoms would form and annihilate. The last photons from those annihilations would travel outward in redshift and cool. The last black holes would evaporate, over timescales measured in exponents of exponents, releasing the last of their mass as Hawking radiation, a slow, incredibly cold trickle of particles and photons, the final output of the universe's last remaining structures. And then, in the dark era, there would be nothing but radiation, a universe of photons and neutrinos and other fundamental particles at a temperature so close to absolute zero that the difference is undetectable by any known means, expanding forever in every direction, growing thinner and colder with every passing eon. 14 billion years ago, this universe began with a density and temperature that no physical instrument could measure. It will end, or rather, it will continue without end, in conditions that are, in their own way, equally extreme, not hot and dense, but cold and thin and empty and dark beyond any darkness we can imagine. Between those two extremes is everything. Every star, every planet, every living thing, every thought, every ocean and mountain and galaxy cluster. Every photon that has ever traveled from a source to a destination and been absorbed or detected or simply lost to the void. Every event that has ever occurred in the physical universe, from the first quantum fluctuations of the inflationary epoch to the last gamma rays from the last positronium atom, is contained in the interval between that first moment and the cold infinite future. And we are here, somewhere in the early pages, looking outward. The universe is old enough to be extraordinary, and young enough that its best years of structural complexity may still be ahead of it. The red dwarf era alone will dwarf everything that has come before. We exist in a window of time that is, cosmically speaking, remarkably brief, but also remarkably rich, a universe still full of stars, still producing light in abundance, still close enough to its origins that the cosmic microwave background is detectable, still structured enough that 2 trillion galaxies fill our observable sky. The last light is coming. It will be a long time arriving. And when it finally fades, when that 1.16 solar mass black dwarf completes the nuclear evolution that has been underway inside it since before the concept of time had any practical meaning, the universe will not notice. It will simply continue, cold and dark and vast, carrying forward the laws of physics that it has always carried, expanding into the nothing that surrounds it, indifferent and complete. We noticed, though. We looked up, and we asked where it was all going, and we followed the physics as far as it would take us. And it took us here, to the last explosion of the last dead star, in a universe 10 to the power of 32,000 years old, in a darkness that has no name and no end. That is, in its own quiet way, something worth knowing.